All right, guys, welcome back. We are moving on into our next section here, which is building a redundant switch topology. When we talk about redundant switch topology, we're talking about having multiple links. Remember, we had that core distribution and access design, and we had multiple layer 2 links as well as multiple layer 3 links that went from the access layer to the distribution layer, and then from the distribution layer to the core layer, and so on, right? But at the access layer, because we're probably going to be running layer 2, having those redundant links will create loops in the topology, and loops in layer 2 are very bad because it will create a high potential, almost a guaranteed potential for broadcast storms and duplicate frames and so on. So in order to have that layer 2 redundancy between the access layer and the distribution layer, we need to run spanning tree. And you can see that's what this section is all about. What is spanning tree? How does spanning tree work? How do we tune the different spanning tree configurations? What is a rapid spanning tree protocol? How is it different from standard spanning tree? And then finally, what is multiple spanning tree? All of these things we discussed in our traditional CCNP route switch course. So we're going to be hitting these topics up again in this particular case in the ENCOR course. Maybe not as much detail, but we'll be taking care of that. So spanning tree is a layer 2 protocol. There are multiple versions of spanning tree, and we'll talk about the different versions as we go through this section here and what the major differences are. But the idea of spanning tree, as you guys are probably aware, is it allows us to have physically redundant layer 2 paths in our topology for failover and redundancy, but at the same time, it ensures that that redundancy is not going to cause a loop in the topology. So spanning tree will go through an election process, what we call the spanning tree algorithm, and it will temporarily disable some of those redundant links so that we only have one active data path for traffic flowing through the network, getting rid of essentially that bridging loop that might exist in the topology. So between switch A and B in this case, we do have a redundant connection. These are not bonded together. We're not using ether channel. We'll talk about that later on in this section here for today's lessons. But we can see that that would cause a loop. And if host X sent out, for example, an ARP request, switch A is going to flood that request out of its interfaces. Switch B will receive that request. And again, switch B is going to flood that traffic as well. Remember, the switch always floods traffic out the interface with the exception of the interface that it came in on. So, for example, it would get flooded if it came in the top port. It would get flooded out of the bottom port, and vice versa. So the traffic would basically loop infinitely across the network. And at layer 2, we don't have a time to live for our Ethernet frames. We have time to lives for our packets, but if it's an ARP request, it's an Ethernet frame. There is no packet per se. ARP doesn't actually get encapsulated inside of IP, so that frame would potentially stay there forever, and it would get flooded over and over again, and the network would eventually just stop working. So we would have these broadcast storms that would bring the network to its knees, basically. We would also see MAC database instability. MAC addresses would constantly move from one interface to the other based on where the frame happened to come in on a particular interface, because we're not going to flood the frame out of every interface. We're going to potentially only send the frame out of the interface that the MAC address is currently tied to. But it's entirely possible that that same MAC address could end up being seen on multiple interfaces, which will definitely impair the switch's ability to make accurate forwarding decisions. And that would cause, really a lot of instability in the overall success of forwarding information across the network. So spanning tree goes through an election process, and we'll learn what that process is, so that we only have one active path through any kind of layer 2 domain. Remember, this is a layer 2 protocol. So when it comes to routing, when it comes to layer 3 boundaries, it's kind of irrelevant, right? Because with routing, we at least have a time to live. And if a packet gets caught in a loop, that time to live value will continue to get decremented until the packet is eventually destroyed, because that value reaches 0. All right. So with the example that we saw above here, spanning tree would go through some sort of process to identify, well, there's about 4 steps, exactly 4 steps actually, that the switches will go through to be able to identify which link, or which port, I should say, would be in a blocking state. There's really only 2 states that ports can be in spanning tree in a stable topology. There's a couple of transitionary states, listening and learning, but ultimately it's either going to be the port is forwarding or the port is blocking, and that's what we're primarily focused on with regard to stabilizing the topology, which ports are forwarding and which ports are blocking. We'll talk about the port states. We'll also talk about the port roles. What is a root port? What is a designated port? What is a non-designated port? And so on. And that's all part of understanding the overall spanning tree algorithm and how the algorithm functions so that we can effectively build this topology. A lot of times what will happen is engineers these days will try to design the spanning tree out of the design as much as possible. And the only way that you can effectively do that is if you design the network to be routed all the way to the edge. We talked about that yesterday a little bit, where you had an option to deploy your access layer as a layer 2 access layer, or as a layer 3 access layer where you're doing routing to the edge. Now, you'll never get rid of spanning tree completely. You always want to run spanning tree just in case somebody happens to plug maybe one port on a switch into another port on a switch by accident. We don't want that broadcast domain to be crippled if that happens, so we still want to run spanning tree in that particular case. But we've at least designed out the need to incorporate a spanning tree topology design in our overall topology. Okay, so let's say that this is our topology here. We've got switch A, switch B, and switch C, and for redundancy purposes, those switches are redundant, or for resiliency purposes, those switches are redundantly connected to each other. So we have clearly a loop in this topology. Now, the very first step in spanning tree is to figure out who is going to be the root. All right. Now, with spanning tree, as you guys probably remember from some of our previous classes, with spanning tree, we elect the root based on one value. And that root is elected based on something called the bridge ID. Now, the bridge ID is a combination of a couple of different things. It's a combination, and we'll see a picture of this in a little bit, but it's a combination of the switch priority value that you configure, which is a value, well, traditionally it's always been kind of a 16-bit value, so it would be something from 0 to 65,535. But with the extended system ID format, we have a limitation of setting the value in increments of 4,096. I'll talk about that a little bit later on as well. But that's a value that you can set as an administrator to identify or to control which switch in the topology becomes the root. All right, the root is how every other spanning tree decision is made. Once I've decided who's going to become the root of the topology, then I will go through the rest of the election process to figure out what my root ports are, what my designated ports are, what my non-designated ports are, and so on. All right, so priority is the way that you can establish which switch becomes the root, but some switches may have the same priority. And so in order for us to ensure that there's never a tie, MAC address would be used as the tiebreaker. So every switch has a MAC address tied to it. It actually has multiple MAC addresses. There's MAC addresses for the switch itself, and then there's MAC addresses on each of the individual ports. But the base MAC address is what allows us to identify essentially a unique ID for that particular switch. So, and again, we'll see a picture of this a little bit later on, but the bridge ID in essence is a combination of switch priority and switch MAC address. All right, now you can't change the MAC address, that's burned into the switch, but we also know that the MAC address, because it is burned in, should be globally unique, right? That's the whole point of a MAC address, is that it's globally unique and it's not shared with any other switch. So there's always going to be some sort of tiebreaker in the event that some of the configurations are similar on the switches themselves. One of the other things to keep in mind as we talk about spanning tree is that lowest always wins in spanning tree. Lowest always wins. Lowest bridge ID, lowest priority, lowest MAC address, lowest interface number. So for example, you might have a tiebreaker where you're trying to decide between, say, which port is going to be used in a particular spanning tree process, and that's going to be based on a tiebreaker, what we call a port priority tiebreaker. So we'll talk about that as well. I mean, obviously we want to make sure that we go through the process of understanding how the algorithm works step by step, and if I have to use a external diagram to describe that process as well, I'll be more than happy to do that. All right, but everything is done. Everything in spanning tree is done after the root bridge is selected. So let's say in this particular case, switch A just happened to have the lowest priority. Maybe the priority was set to 4096, and switch B and C had a priority of 8192. Switch A automatically becomes the root. All right, it's very simple. That's the very first decision we make. Whichever switch has the lowest bridge ID becomes the root, and there's never a tie. Even if you set the priorities to be the same, the MAC address is always going to be the tiebreaker, and lowest MAC address wins in that particular case. Once I've elected the root, I then go through and I decide what the status of all the other ports in the topology are going to be based on that root bridge selection. So switch A becomes the root, switch B and C become kind of non-root bridges, if you will, and they have to decide how they're going to communicate to that root. So switch C is going to say, okay, my best path to the root is this top link here. And switch B is going to say my best path to the root is this top link here. That's going to be based on what we call path cost. And there are some predefined cost values in spanning tree that allow us to define essentially the best path to the root. And those ports become root ports. So that's the second election that takes place, or the second part of the spanning tree process, is to select a root port. We only select root ports on switches that are not the root bridge. There are never any root ports on the root bridge. All the ports on the root bridge are going to be designated. We'll talk about that in a second. So again, step one, go ahead and select who the root is going to be. That root bridge is the reference point for all other selections in the topology. And then we select the root port on all of our non-root bridges. Now it says here by definition, one port on each non-root bridge. One port, a single interface. And by the way, spanning tree is a layer 2 protocol. So this election is happening per VLAN. Right? Cisco implements spanning tree on a per VLAN basis. Now you could have all the VLANs match by setting the priorities for each of the VLANs to be the same, or you can control who becomes the root for a particular VLAN by manipulating the priority per VLAN on each of those switches. So I could make switch A the root for VLAN 10. I can make switch B the root for VLAN 20, etc. by manipulating the priority values per VLAN. All right. Now it says here we select a root port on a single root port on any of my non-root bridges. The term bridge is synonymous with switch. Spanning tree's been around since the old digital corporation days when we had bridges that allowed us to segment our network so we could make layer 2 forwarding decisions and make the network more efficient. Rather than having a single collision domain, we could have kind of separate collision domains. But so when you see the term bridge, it's just really synonymous with switch in this case. So how do we pick what port becomes the root port? It's based on cumulative path cost. So let's say, for example, in this particular case, all of these links are 100 megs, all right? And we're using the traditional path cost values that IEEE specifies in the original version of Spanning Tree. So the cost of a 100 meg link is 19. That's a fixed value. We'll see those values a little bit later on, but that's a fixed value that was determined when the protocol was defined. The RFC for Spanning Tree was defined. They said, okay, 100 meg links are going to cost you 19. 10 meg links are going to cost you 100. And as the speed goes up, the cost goes down, which makes sense, right? So let's say all these links are 100 meg. If switch A was to go, switch C was to go directly to switch A, that would be a cost of 19. If switch C was to go through switch B, that would be a cost of 19 times 2, right? Because again, it's cumulative path cost for each of the links. So I'd have 19 plus 19, which is 48, right? And 48 is a higher cost than 19. So that port, that top port, becomes the root port. On switch B, we do the same. We make the same decision. What's the least cost path to the root? And that would become the root port on that particular switch. Every non-root bridge or every non-root switch is going to have at least one root port per VLAN. It could be the same port for each VLAN, or it could be a different port for the VLAN. It just depends on how you've manipulated Spanning Tree on a per VLAN basis. But every single port is going to have the same. I mean, every single bridge is going to have at least one root port per VLAN. Okay. All right. So that's step number 2. We select the root port. Now that's the port role. There's a difference between port role and port state. Port role indicates its function within the Spanning Tree topology, like root port, designated port, non-designated port, alternate port, backup port. These are what we define as port roles. Port states is the port forwarding or is the port blocking. And ultimately, those are the only two states that a port is going to end up in, is in a blocking state or a forwarding state. In rapid Spanning Tree, they don't call it blocking, they call it discarding. But it's the same concept, right? The port is receiving BPDUs and processing BPDUs, but it's not processing or forwarding traffic for the clients. So there's a distinct difference between port role and port state. The role is its function within the topology. The state is actually what it's is the data forwarding, or is the port forwarding or not forwarding? All right. So that's what we talk about in that particular case. And again, we'll see some more of this as we go through the rest of the chapter. I'm just trying to give you as much information right now as possible, so that you'll see it multiple times as we go through the section here. So step number 2 was to elect the root ports. Now step 3 is what we call our designated port. So designated port is a port role. The state of designated ports is forwarding. And it's quite simple. Designated ports are they're ports that are put into a forwarding state, and there is at least one designated, well, not at least, there is one designated port per LAN segment. So in this particular topology, we have 3 LAN segments, which means we're going to have 3 designated ports. All right. Now, let's say, for example, between switch C and switch A, that is a segment. Between switch A and switch B, that is a segment. Between switch C and switch B, that is a segment. So we're going to have 3 designated ports in this particular case. Root ports can never be designated. So a port is either a root port or it's a designated port, but it's not both. All right, so root ports can never be designated. They're either, like I said, a root port or they're a designated port. So how do I decide on those segments with root ports which port becomes designated? Well, it's basically just the other side, right? But it's there's actually a decision process that's used to decide which side becomes designated. And it's based on the bridge IDs of the 2 switches that share that common segment. So switch A has a bridge ID, switch C has a bridge ID. Whichever one is the lowest, that becomes the designated side. Does that make sense? So I'm comparing the bridge IDs to the 2 switches that are connected to the segment, and I'm saying, okay, whichever side has the lowest bridge ID, that is the side that becomes designated. Well, the root switch is never going to lose that because the root switch is the root because it has the lowest bridge ID of the entire layer 2 domain. So all ports on the root are always going to be designated. There's no exception to that rule. Every single port per VLAN on the root for that particular VLAN is going to be a designated port. But what about the link between switch C and switch B? How do I decide which side is going to be designated in this particular case? Switch C, in this particular case, has a lower bridge ID than switch B, so switch C becomes the designated side. Does that make sense? The idea is that eventually we'll get to the point where we've identified a port or multiple ports in the topology that are going to be blocking. So far, all we've seen is what is forwarding, what ports are forwarding, the root ports and the designated ports. Which brings us now to the final step, the 4th step in the process, which is whatever remains becomes non-designated and that port goes into a blocking state. All right? So overall, the spanning tree election process is fairly straightforward. Number 1, elect the root based on the lowest bridge ID. Number 2, on all of the non-root bridges, elect the root port, which is the port that is connected to the least cost path to the root. And that's based on static cost values that are predefined within the protocol. Step 3, on every segment, we have a designated port. That designated port is the port that's attached to the bridge with the lowest bridge ID for that segment. And then finally, step 4, the remaining ports are blocking. All right? So that's what they're saying in the kind of the last paragraph there. Ports that are neither root or designated must be non-designated. And non-designated ports are normally in the blocking state to break the loop. Okay? Now that non-designated port could transition to a forwarding state if, for example, other ports in the topology fail and we have to go through the re-election process again. All right? The diagram here is a little anemic because it doesn't really have any of the values that we would use to describe the overall process. Like it doesn't have priority values on the diagram, it doesn't have MAC addresses. So hopefully it makes sense, and like I said, I'll be more than happy to kind of expand on it if you guys have any questions about it. But hopefully it makes a little bit of sense. All right, so what is a root port? The root port exists on all non-root bridges. It is the switch port with the best path cost to the root bridge, root port forward traffic towards the root, and the source MAC address of the frames that are received on that root port allows us, whatever source MAC address we receive, we do learning, right? What they're basically saying here is if I receive data frames on a root port, I'm going to go ahead and update my CAM table, and I'm going to basically treat that port as a standard forwarding port. All right, only one root port is allowed per bridge. That's not entirely true. It is true if you add the keywords per VLAN, right? So you could have more than one root port on a switch if you have multiple VLANs, and those VLANs are potentially configured differently with regard to spanning tree. So you could have more than one root port, but within a VLAN, you can only have one root port per switch. The designated port. This port exists on the root and non-root bridges. For the root bridge, all the ports are automatically designated, which makes sense because it's never going to lose that election, right? It is the root because it has the lowest bridge ID. So it's never going to lose that election. For non-root bridges, a designated port is the switch port that will receive and forward frames towards the root bridge as needed. That's how they define it, and that's typically how it's defined in most documentation. I find it easier just to simply say, look, if I have two switches connected to a segment, whichever switch has the lowest bridge ID is the switch that's going to have the designated port. And that's usually 99.9% of the time, that usually will allow you to select that designated port very easily. Because if it's a shared segment, it's different. But if it's a point-to-point segment between two switches, then that's a very simple comment, right? Hey, I got two switches that are connected to each other with a cable. Which switch has the lowest bridge ID? That's the designated port, okay? Only one designated port is allowed per segment. If multiple switches exist on the same segment, an election process determines that designated switch, and the corresponding switch port begins forwarding frames. How would I have more than two switches on a particular segment? That's entirely possible if you have a shared link, right? So maybe we have a hub. I mean, this typically wouldn't happen, but maybe we have a hub, and that hub allows us to connect 5 or 6 different switches together, and then now we have to decide which ports are designated based on an election process in that particular case. So that's entirely possible. Although not probable because we don't typically put hubs in our networks these days. All right, so for me, I think it's just simpler just to describe the designated port as the port that's connected to the switch with the lowest bridge ID. Non-designated ports are basically just the ports that are blocking. Now, when we say blocking, it doesn't mean that the port is actually physically shut down. It doesn't mean the port is error disabled. It just means that the port is not processing frames for clients. Blocking ports still accept Bpdus. We'll talk about what those are in a minute. They don't send Bpdus, but they will accept Bpdus, and they do not process or forward frames from clients. So in essence, the port is disabled, but you wouldn't be able to tell for like if you did a show interface or show IP interface brief, you wouldn't be able to tell whether or not a port is a non-designated port from that perspective. You would actually have to look at the spanning tree information, right? Show spanning tree or some other method of verifying whether spanning tree topologies and spanning tree configurations. All right. In a redundant topology, which of the following is a problem where multiple copies of the same unicast frames are delivered to a destination station, causing problems with the receiving protocol? Well, there's a couple of things that could happen here. The question's not worded very well, or it's kind of worded poorly, but Which of the following is a problem where multiple copies of the same frame are delivered to a destination station? That could be a broadcast storm, right? If we have lots and lots of copies of the same information being delivered, or it could result in MAC database instability. It depends on how you're interpreting the question itself, right? If it's just a couple of copies of the frame, then we may see just simply MAC instability. But if it's, you know, a flooding of frames, then we would say, yeah, that could be related to a broadcast storm or whatnot. But we know what loops in a layer 2 topology will do. It'll basically bring down the network. Ultimately, that's what we're concerned with. Okay? So I've mentioned Bpdu multiple times. Bpdu stands for Bridge Protocol Data Unit. Bpdu is a layer 2 frame that allows, well, basically it's the information that spanning tree uses to make decisions, right? So it's the actual frame that gets generated that switches will receive and process to determine what the topology is going to look like, what the network's going to look like, is based on these Bpdus. And we can see there are several different fields within a Bpdu. Some slight differences if you talk about different versions of Bpdus. There are some differences between Bpdus. Bpdu formats are slightly different. If you're running, for example, multiple spanning tree versus rapid spanning tree versus common spanning tree or 802.1d. Overall, though, the Bpdu is generally the same, right? You've got the version field. The protocol ID identifies spanning tree. The version indicates the version of the protocol. So am I running rapid spanning tree? Am I running multiple spanning tree? Whatever it might be. Then we have the message type. And the message type will identify whether or not this is a topology change notification Bpdu or an initial convergence Bpdu, right? So the switches will try to converge using standard Bpdus, which is just basically a switch sending out the information related to the configuration of the switch itself. Or we have triggered Bpdus. And triggered Bpdus will be Bpdus that are sent out based on a change in the actual topology. The link state changed on an interface. Maybe a port that was in a forwarding state went down. That's going to trigger a topology change notification so that the spanning tree algorithm can run and we can decide what the new topology is going to look like based on that change in the existing topology. All right. We have some flags that are used to indicate various transactional events that occur with spanning tree. The root bridge ID, which allows us to identify the root itself, right? What is the root bridge ID? In fact, let me go ahead and do this. Let me pull up a Wireshark capture of a Bpdu real quick, because it might be easier to understand what these values look like if we're actually looking at an actual capture. So here's a bunch of different spanning tree Bpdus that we've captured here. So if I open up one of these, first of all, we can see that it's encapsulated inside of 802.3 Ethernet. Remember I said that yesterday, basically two different types of Ethernet, Ethernet 2 and 802.3 Ethernet. Ethernet 2 is typically used by, for standard layer 2 communications by clients, and 802.3 Ethernet is going to be used for things like CDP and spanning tree and so on. Not really much of a difference. The only difference is we have a length field instead of a type field, but we do have the type values specified here in what we call the DSAP and the SSAP. Remember, 802.3 Ethernet is the one that has the MAC sublayer and the LLC sublayer, and that's what we're seeing here. But if I come in here and I look at the Bpdu, we can see that this is a Bpdu for spanning tree protocol. The protocol ID is spanning tree, which is essentially, basically, we're saying regular spanning tree in this particular case. We'll talk about the different versions of spanning tree in a little bit. This is a configuration Bpdu as opposed to a topology change notification Bpdu. So again, this is a Bpdu that's sent during the convergence process, not because of some sort of topology change that caused a triggered Bpdu. Let me see if I have a one that's not a configuration Bpdu. Let me see here. So we'll go here and we'll say apply filter and not selected. No, we don't have any in this particular case. So, but basically they look the same. There's really not a huge difference between a configuration Bpdu and a topology change Bpdu. But you know, you might see some flags that are set a little bit differently. For example, is this a topology change Bpdu? That flag would get set to 1. Is this an acknowledgement to that topology change? That flag would be set to 1 if a switch is acknowledging, hey, I got your topology change information, thank you very much, right? And then we see what's really kind of the most important piece of this, the routes information, my information, what is the cost to get to the route, what port number am I using to get there, and then we'll talk about these timers as well. So the route ID is the routes information. Notice there are 3 things that we see. This is in essence the bridge ID for the actual switch itself. This is the bridge ID. 32768 is the priority for the switch, which by the way happens to be the default. All Cisco switches, in fact, even non-Cisco switches, use 32768 as their default priority. Remember, the lowest number wins in spanning tree. So the lower the priority, the more likely the switch is going to become the root. The 100 indicates the VLAN. When spanning tree was originally developed, it was what we called a common spanning tree protocol. And VLAN was not part of the bridge ID format. In fact, we had 2 values in the bridge ID. We had priority and MAC address. When Cisco developed their version of spanning tree, called per VLAN spanning tree, they changed the field. They took that 16-bit priority field and they broke it up into 2 pieces. 4 bits for the priority, which we can actually see here. Well, we can't actually see it, but if you highlight the priority, you can see that it is a an 8-bit field in this particular case. I'm not sure why it's being referenced as an 8-bit field because it should only be 4 bits. And then the extended system ID section would be 12 bits. I'm not sure why it's highlighted that way. Yeah, it kind of overlaps a little bit. You can see how 32768 has the 80 and the 100 includes the 80. But if you look at an extended system ID, let me pull this up real quick. If you look at the format of an extended system ID, this was kind of the original, this was the original format of a bridge ID. You had 2 bytes for priority and then you had MAC address. What Cisco did to run per VLAN spanning tree is they took that 2-byte field and they broke it up into 2 pieces. 4 bits for the priority, 12 bits for the extended system ID. Why 12 bits? Well, guess what? That's where the VLAN goes. Because we wanted to be able to identify that this was a Bpdu for VLAN 10, or this is a Bpdu for VLAN 100, or whatever it might be. Well, VLAN ID fields in .1Q tags and just VLANs in general is a 12-bit value, so that's why they did that. This still provides us, we don't have 65,536 choices for priority anymore. We only have 4 bits for priority, But that gives us still 16 different priorities that we can use in the process. So by adding this system ID extension, we're able to now identify that this is a Bpdu for VLAN 100. And the priority for VLAN 100 is 32.768, but on this same switch, the priority for VLAN 10 might be different, which means that the topology would look differently, right? And this is what we reference as per VLAN spanning tree. The MAC address is just the MAC address. That's my 6-byte field that allows me to identify the MAC address. All right, so really, within the VLAN, this system ID extension is kind of irrelevant because everybody within the VLAN is going to have the same value there because it's spanning tree within that particular VLAN. So again, the election still kind of just comes down to what is the priority and what is the MAC address, right? The VLAN number is kind of irrelevant. So this is the root's information. This is my information. This is the information that I use to reach the root. Not to reach the root, that I use to identify myself. How come I did not become the root? Well, in this particular case, we both had the same priority, but my MAC address is higher than your MAC address. 001 Charlie 0E, same OUI, 877885. So 85 is higher than 78, and lowest always wins in spanning tree. So the tiebreaker in this case is what decided which switch was going to be the root. Okay? So it's just very interesting. We don't typically want to rely on the MAC address to determine what our spanning tree topology is going to look like, because usually the older switches are going to have the lower MAC addresses and the newer switches are going to have the higher MAC addresses. And generally that's probably not, those are probably not the switches that you want to be the root in your topology. Okay. All right. So breaking this down, you can see how breaking it down in Wireshark is a little bit better than looking at it in, you know, kind of as just a picture of a frame. What about this value here? Root path cost. Okay. So basically this switch is saying, look, I know how to get to the root. And I use this interface to get to the root, which, by the way, is a hexadecimal representation of the port priority and port number. When we go into the lab, I'll show you what I mean by that. Hex 8004 is actually converted to the port priority and the port number, which happens to be the 5th port on the switch in this particular case. Actually, it would be the 5th port on the switch. I'll explain what I mean by that when we're looking at the lab exercise a little bit later on. But in essence, this is a gig interface. The root path cost is 4, but it doesn't guarantee that it's a gig interface, but most likely it is. It could be a couple of 10 gigs, but, you know, because it could be 10 gig interfaces have a cost of 2, so it could be a couple of 10 gig interfaces, but most likely it's a gig interface with a cost of 4. Okay. The other values here, message age, max age, hello time, forwarding delay, we'll talk about those. These are all related to the timers that are used in the spanning tree election process. The forwarding delay timer is how long we're going to stay in a listening and learning state as we're kind of transitioning through the whole election process. The hello time is how often Bpdus are going to be sent out, and the max age time is how long I'm going to wait, in essence, for a Bpdu before I decide that the port isn't receiving Bpdus and I go through the rest of the election process. So I always encourage people when you're dealing with protocols and you're trying to learn about different protocols to take the time to look at a Wireshark capture, because if you can interpret or look at each of those fields in a Wireshark capture and kind of understand how they break down and how they're utilized. It makes it much easier to understand how the protocol functions. Yeah, you can look at the frame format like we see here, but you're not really seeing the raw data that's included in the frame, and so you can't kind of correlate that to the actual information that's being exchanged by the devices themselves. All right. All right. So we have a switch sends out Bpdus on the port. The source MAC address of that port and the destination the source MAC address is the MAC address that's used for the Bpdu. The destination address is a standard multicast MAC address, 0180 Charlie 2. And if we go over to our Wireshark capture, we can see that here. This is the source MAC address and the destination MAC address, 0180 Charlie 2. That MAC address is actually used for more than just spanning tree, but it is kind of one of those well-known MAC addresses that's used for lots of different layer 2 types of communication. So there are 3 types of Bpdus. There's a configuration Bpdu, which is basically, they all have essentially the same format. It's whether or not the flags are set. Those 2 flags that we saw for topology change notification and topology change acknowledgement. But overall, the Bpdus are formatted exactly the same way. The configuration Bpdu is what's used for the initial convergence, and then the topology change notification Bpdus are used to identify that a topology change occurred. Now, how that topology change is propagated will depend on what type of spanning tree you're running. The diagram that we see here is kind of the original version of spanning tree. Rapid spanning tree operates much differently, primarily so that it can converge much faster than standard spanning tree. In the past, the switch that originated the topology change, so a link goes down on the bottom right switch there, it's going to send a topology change notification towards the root. The root is then going to send a topology change acknowledgement back to the switch that originated that topology change, and then the root is then going to be responsible for forwarding that topology change information to the rest of the network. You can probably imagine with potentially tens or 20s of switches or even hundreds of switches, if we utilize this method to propagate change information, the convergence time is going to be pretty significant. And that is in fact the problem with the original version of spanning tree. It takes forever to converge. So the topology change propagation process for rapid spanning tree is significantly different. We do not send the topology change information to the root. It is basically flooded from wherever that topology change occurred to everybody else within the topology, if that makes sense. Maybe we'll see something like that a little bit later on. If not, I'll maybe bring up something else and show you guys what I'm talking about. All right. But regardless, a topology change means that something in the network changed, which requires everybody to kind of figure out, is the topology going to be different? Or is a forwarding port now going to become a non-designated blocking port? Or is a blocking port going to become a designated port? Or even possibly did the root change, right? Maybe the root switch went down and we have to elect a new root. Okay? The root bridge is chosen based on bridge ID, like I mentioned. Each switch has its own unique bridge ID. This is the traditional bridge ID format, which includes a 32-bit field for bridge priority, a 16-bit field for bridge priority, and a 48-bit field for MAC address, right? 6 bytes for MAC address. Now the MAC address is burned into the switch, so we can't really modify that. That's going to be unique for every switch, which is good. That's important for us to be able to have tiebreakers. but the priority field is a value that you can set as the administrator. Anywhere from 0 to 65,535, the default priority is 32,768. The lowest possible value is 0. Now it says here, and this is incorrect, but it says here, priorities start at 0 and they can be modified in increments of 4,096. That is true if you're using the extended system ID format. So they're kind of mixing terms here. If you're not using the extended system ID format, you can set the priority value to any value from 0 to 65,535. But if you're using the extended system ID format, which breaks this field up into two pieces, there's a reason why you have to set the value in increments of 4,096. Because what they did is they wanted to make sure that this was backwards compatible with the new extended system ID format was backwards compatible with traditional bridge ID formats. So rather than start the numbering of the fields back at 0 or 1, they left the values of these 4 bits to their original value. So this is now the new priority field. This is the extended system ID extension, which is basically the VLAN. But notice they went from 2048 to 4096 to 8192. So these are the only possible values that you can have for the priority if you're using the extended system ID format. So the minimum priority you can have is 0. The next value you can set, which would be a 0001, binarily, 0001 would mean that you have a priority of 4096, 0010, 8192, and so on. That makes sense. So that's what they mean by you can do it in increments of 4096. With this particular format, that's not a limitation. If you have a single range here. Now they're kind of mixing it up here a little bit because they see 32,768 plus the VLAN number. This field should really be kind of broken up to indicate that we're using that extended system ID format. Because the priority, yes, it includes the VLAN, but for every switch in the same VLAN, that value, that portion of the value is always going to be the same, right? Because if it's VLAN 100, everybody's going to have the same first 12 bits in that field. All right? In any event, the lowest value wins. So any switch that has the lowest value is going to end up being the root for that particular VLAN. If the switches have, all the switches or some of the switches in the topology have the same priority, then we would use the MAC address as the tiebreaker. Okay? So in the beginning, every switch kind of assumes it's the root until it starts propagating Bpdus. And so during the election process, there are deterministic timers that Spanning Tree uses to ensure that we have enough time to collect the Bpdus to make sure that we're making the right decision on who becomes the root, right? We don't just automatically, within 2 seconds or 4 seconds or whatever, figure out what the topology is going to be. It's going to be 30, potentially 15 to 30 seconds to determine who the root is going to be in the topology, maybe up to 50 seconds in some cases, right? So in this particular case, again, switch 1, or switch 2 in this case, became the root because it has the lowest bridge ID, and then we go through the election process and we converge, all right? Now there is a bit of a polarma here, if you will, in that we have kind of a tiebreaker on switch 3. There are multiple tiebreakers that could exist when you're talking about selecting your designated ports, okay? So let's talk about, let's assume that switch 2 is the root because it had the lowest priority. We can also see that these are all Ethernet ports and they all have a cost of 100. Again, fast Ethernet is a cost of 19 in the traditional sense. There's some newer cost values that Spanning Tree has, or IEEE has defined for kind of more modern networks where we might have 10 gig links and 40 gig links and terabit links and so on. But traditionally, 100 meg links cost us 19, 10 meg links cost us 100. So from switch 1's perspective, it's very easy to identify who the root port's going to be, because if I go down here and I go up, it's going to cost me 200. But if I simply go this way, it's going to cost me 100, so that becomes the root port. We also know that every port on the root is designated, which means they're in a forwarding state, because every segment has a designated port. Between switch 1 and switch 3, we can't really tell which side is designated because I don't see the priority values or the MAC addresses. But one of these ports on this link here is going to become designated. One of those ports is going to become blocking, right? Or non-designated. But what about the links between switch 3 and switch 2? We have a tie, right? This top link, this is not an ether channel, so these links are not bonded together. The top link has a cost of 100. The bottom link has a cost of 100. How do we break that tie? It's based on the advertised port priority and port number of the neighboring switch. It's not based on my values. I'm not choosing my root port based on the lowest port number here. I'm typically choosing the root port based on the lowest port number from the neighboring side. Because again, it's all about if something changes in the topology, what is likely going to be the next topology, right? In other words, if port 2 goes down, port 2 on switch 3 goes down, then nothing really changes because it was already a blocking port anyway based on the election that we had. All right. So the port priority, which is 128, that is very similar to a switch priority. It's a value that you can configure on the interface. And that's an interface configuration level command. I can actually go into the interface and set per VLAN the priority value of an interface. So I can influence the overall path selection process by manipulating the port priority. The dot and then the number, this is the interface number. That is a fixed value. It's almost kind of like a MAC address value. You can't really change it because it's just simply based on what is the actual port number. Remember we saw in the Bpdu capture the 8004? Well, guess what? That was this value right here, 128. Let me see here. If I go into Notepad, 128.4. If I was to take those values, 128.4, and I was to convert them to hexadecimal, assuming that we're using a 16-bit field, right? Which we would be if it's a 4. Remember we had 0x8004. So the 8000 represent, or the 80 represents the 128, and the 04 represents the 4, right? Because 80 in hex would be 1000000, which equals 128, and 04 in hex would be 1234 1234, which would equal the interface number. So that's how they're getting that hex 8004 from the port priority and number field. All right. This value you can't really change. That's statically assigned to the port, but this is a value that you can modify. And because it is a 8-bit value, you can imagine that you can set it within that range, right, from 0 to 255. But it also has to be in specific increments because that's limited as well. We'll see that maybe a little bit later on. So that's a tiebreaker. There's a couple of other tiebreakers that exist as well. Hopefully we'll see those as we kind of go through the process here. All right. After the root bridge is elected, each non-root bridge must figure out where it is in relation to the root bridge. The root port is the port with the best path to the root. And remember I said we had some kind of legacy values and we had some more modern values that came out in 2004. We see these values assigned here. This is by IEEE because this is an 802 standard, right? Meaning an IEEE standard. 10 gig costs you 2 gig costs you 3, 1 gig costs you 4. Remember I said before we saw that cost here, we see a cost to the root. In this case, to get to the root, it's a path cost of 4. I can't assume that that is simply a gig link. It's likely. I mean, that's typical in a network. But it could be a couple of 10 gig links that are back to back, right? Maybe the switch is 2 hops away, and I just happen to have 2 10 gig links that get me there. That would still be a cost of 4 in that particular case. But these are cost values that are assigned to each of the different speeds, and these aren't the only cost values that we have. These are just some of the common ones that we would see. They've obviously modified this because we're now starting to see links that are actually faster than 10 gig. So we need to make sure that we're representing those faster ports with a lower path cost so that we can accurately determine the best path to the root. All right. I want to be clear though. We don't have to send our traffic to the root, right? If let me go back to this topology diagram. Let's say, for example, a device in switch, well, in this case, it would have to be the case, but a device in switch 1 wants to talk to a device in switch 3 because this link is not going to be active. The traffic would have to flow through the root. But let's assume there was another switch over here connected to switch 1. Doesn't mean that I have to send the traffic to the root and then have the root forward the traffic back to switch 1. Once the topology is determined, and we've identified which ports are forwarding, which ports are blocking, normal switch operation takes place. Normal forwarding operations take place. I forward based on how I learn MAC addresses, what ports MAC addresses exist on, etc. Right? Does that make sense? Dangled a preposition there, but sorry about that. But you get what I'm saying, right? The traffic doesn't necessarily have to flow through the root, but we have to have an organized way of determining the best possible topology for forwarding ports and blocking ports. So there has to be some sort of algorithm that allows us to do that. Okay? So as I mentioned, once we've elected the root, the next step is to go to my designated ports. Now, we know that all the ports on the root are going to be designated because it's never going to lose, right? The bridge with the lowest bridge ID on the segment is always going to be the designated side. Now we see some values for switch 1 and switch 2. Switch 1 became designated because it has a lower MAC address than switch 3. Make sense? So I compare the bridge IDs of the two switches that share a common segment, and the switch with the lowest bridge ID becomes the designated side. That's not usually how they describe the designated port election process in most documentation. They say, well, the designated port is whichever port is necessary for us to be forwarding towards the root. It doesn't make a whole lot of sense when you look at this diagram because the root port is port 00 on switch 1, not port 01. So for me, I always just say, look, it's whichever interface is connected to the switch with the lowest bridge ID for that particular segment. All right. We already determined that this was the root port for this switch based on the advertised port priority information from the neighbor. And because this side is designated, this side becomes non-designated. So this is my blocking port, this is my blocking port, and I'm pretty much done with the election process. Okay? All right. You can have two paths with an equal cost to the root bridge. We saw that with the two links that went from switch 2 to switch 3, right? And we had to decide what the tiebreaker was. Certainly the lowest root path cost to the root bridge becomes a forwarding port. The lowest sender bridge ID, the lowest sender port. So we talked about number 3, the lowest sender port, right? So in this case, 01 is going to have a lower port number. These ports both have the same default priority of 128. So port 1 is going to have the lower number. That's the lowest sender port. That becomes the root port. But what happens if I have a scenario, because they don't have a diagram for this. What happens if I have a scenario where I have my switches here, right? And all these links are the same speed. And this switch here becomes the root. For this switch here, do I decide to go this way or do I decide to go that way to get to the root, right? So now there's another tie. There's another tie here. Assuming all the links are the exact same speed. So our path costs are the same in this case. This is the second tiebreaker that they're talking about in the book. We go to the switch that has the lowest bridge ID. So each of these switches, each of these switches are advertising their bridge ID to the downstream switch. Whichever one has the lowest bridge ID, let's say it's this one, that's going to be the way I go. So I'm comparing the bridge ID between these two switches here, and I choose the switch with the lowest bridge ID. That's the tiebreaker in that scenario. And that's what they're describing in this particular case, the lowest sender bridge ID. So those two switches are telling me what their bridge ID is. I'm just going to choose the lowest because, again, it's about what if there is a topology change, what's the next likely topology going to be, right? Because I'm trying to make sure that I'm kind of following an election process that's going to ensure the quickest election based on any changes that occur. Okay. So in this example, switch 2 becomes the root. All of its ports are designated to prevent loops. We do our blocking ports on switch 1 and switch 3. We've gone through the election process. We understand how that works. All right. Now, with regard to port states, like I said, there are two things that we decide in spanning tree. What is the role of a port, designated, non-designated, root, etc., versus what is the state of the port. And two states that we know exist are forwarding and discarding, or forwarding and blocking, right? So those would be the two states that kind of exist by default. Once spanning tree has done its election, is the port forwarding or is it blocking? But we also have a couple of transitionary states. Now this will depend on the type of spanning tree that you're running. Every version of spanning tree has a learning state. The 802.1d, 802.1s, 802.1w all have learning states. A port that is in the learning state is actually blocking. It's not forwarding traffic. But it is updating the CAM table. So the whole term learning simply means I'm still trying to figure out what the topology is going to look like. So I'm waiting for Bpdus, and I'm processing Bpdus. I'm not yet forwarding data, but if I happen to receive an Ethernet frame, I'm going to take the source MAC address of that frame, and I'm going to update my CAM table so that when I do decide to go into a forwarding state, I've already learned the information about the clients, right? But a port that is in the learning state is still not forwarding those frames or sending out or receiving frames. We're sending and receiving Bpdus, but we're not sending and receiving traffic, client traffic. Make sense? The difference between the learning state and the listening state is in the listening state, we're just simply not updating the CAM table. So the listening state is I'm sending and receiving Bpdus. I'm trying to figure out what the topology is going to look like, but I'm still not updating the CAM table. And remember that forwarding delay timer that we saw in our Bpdu? At the very end, we see this forwarding delay timer, which happens to be in seconds. That is the timer that indicates how long we stay in the listening and learning state. Right? So for 15 seconds, I'm going to be in the listening state. For 15 seconds, I'm going to be in the learning state. And then I'll transition either to the forwarding state or the blocking state, depending on what the port role is. All right? So it's kind of an interesting process. If Cisco does like to define disabled as a state. If you look at the description here, it's kind of interesting, I guess. It says this port is administratively shut down, which means it's not running spanning tree. So how can that be an actual mode if it's not running spanning tree? I've always had kind of an issue with that definition, but it's in all the documentation. You see it everywhere. Disabled means the port is not running. It's not working. However, if the port was turned on, it would most likely cause a TCN, and it would start running the spanning tree process. Blocking state, very simple state. That means the port is receiving Bpdus, but not sending Bpdus, not learning MAC addresses, not forwarding data. The forwarding state, also easy, it's doing everything, right? It's sending Bpdus, it's receiving Bpdus, it's learning MAC addresses, it's forwarding data. Both the listening and learning state were receiving Bpdus, we're sending Bpdus, listening we're not updating our CAM table, learning we are, but we're not forwarding traffic in those states as well. So it's very important distinction, and you'll see this on the exam as well, the difference between what is a port state and what is a port role. All right, and we'll talk about different versions of spanning tree a little bit later on, and because some of these states and roles are different depending on the version of spanning tree that you have. All right. In the spanning tree protocol, which of the two port types are able to forward traffic? That would be a root port and a designated port. There is no such thing as, I guess there is such thing as a listening port. That's a transitionary state. The port never stays in listening. The disabled, of course, wouldn't be doing anything, and blocking, obviously, is blocking. In the spanning tree protocol, which port on a non-root switch is the closest logical port to the root? That would be our root port, right? That's the least cost path to the root, is how we define that. If two switches have the same bridge priority, which of the following options is used as a tiebreaker to determine the root bridge? That would be the MAC address, right? That's the only tiebreaker that we can have in that particular case, is the MAC address. So the last section that we're going to talk about before we break for lunch is what are the different spanning tree protocol types, and what are the features of each of these protocols. There are several different types of spanning tree variants. You have the original version of spanning tree, which is called CST, or 802.1D. The D stands for don't use this version of spanning tree. Because it's very slow, convergence times are very long, and it is a common spanning tree protocol, which means that if you have 100 VLANs in your topology, all 100 VLANs have to assume the same topology, meaning that the root for one VLAN needs to be the root for all the VLANs. there is no control or no option to change the spanning tree election process per VLAN. Okay, and that's 802.1d. Now Cisco came up with their own version of 802.1d called PVST Plus, per VLAN spanning tree. It's still not a very good version of spanning tree because it uses the same topology change notification process that 802.1d did, which means it's very slow to converge. But you could at least manipulate the spanning tree election process on a per VLAN basis. So this is where the extended system ID came out, and you were able to now manipulate spanning tree on a per VLAN basis. The plus piece was really kind of one of the most important changes that was made. I guess being able to manipulate spanning tree per VLAN was kind of important as well, but the plus piece is where Cisco added things like PortFast, Bpdu guard, root guard, loop guard, backbone fast, uplink fast. So Cisco basically said, you know what, spanning tree is a great protocol, but there's a lot of deficiencies from a security perspective and from an operational perspective. Let's go ahead and enhance the protocol with a whole bunch of special tools and special configurations. That's where the plus comes into play, right? So Cisco kind of came up with all these enhancements to spanning tree to make it operate a little bit more securely and a little bit more efficiently. The next spanning tree that kind of came out was 802.1w. What I refer to affectionately as WAPID spanning tree. This is the rapid spanning tree protocol. The W doesn't stand for rapid, but I always call it WAPID because it makes it easy to remember. But basically what they did with rapid spanning tree, and it's PVRST Plus or per VLAN rapid spanning tree for Cisco's version, or 802.1w for the IEEE version. But what they basically did in this case is they said, let's go ahead and come up with a different way of disseminating topology change information. So rather than having to send a topology change notification all the way up to the root, have the root send an acknowledgement, and then have the root propagate that topology change information to the rest of the network, let's go ahead and just simply send the topology change notification information from the switch that originated the change to all the other switches in the topology and let it kind of propagate through the network that way, which made it much, much faster, right? Now there's a couple of other differences that they have with rapid spanning tree. They added 2 additional port types, an alternate port and a backup port. Both of those are blocking ports, but it's kind of like the whole concept of successor, feasible successor in EIGRP. I pick the root port, which is the best path to the root, but then I go ahead and choose my alternate port, which is the next best path to the root. And if the root port fails, I can immediately start using the alternate port in my spanning tree topology to speed up convergence. And it's pretty significant. We go from possibly a 50-second convergence window down to a 2 to 3 second convergence window with rapid spanning tree. So it's pretty significant in a change in that regard. They also renamed the blocking port to discarding. There's a couple of other changes as well. Okay. And that's what the RPVST Plus is. That's Cisco's enhancement of 802.1w. And then we have 802.1s, which was actually what I call multi-instance spanning tree or multiple spanning tree. We're going to have a whole section on that a little bit later on, but the problem with spanning tree is that if you have 100 VLANs and you're running Cisco's version of spanning tree, you're going to have 100 different instances of spanning tree running in your topology. That means 100 different Bpdus every 2 seconds per VLAN, right? Well, not per VLAN, but 100 total Bpdus because you have 100 VLANs, if that makes sense. So a lot of traffic being generated, but ultimately, even if you have 100 VLANs, you're probably only going to have a couple of different topologies, right? You're probably going to have one distribution switch that is going to be the root for 50 VLANs, and the other distribution switch is going to be a root for the other 50 VLANs. And so you only really have 2 topologies, but you're running 100 instances of spanning tree. So what multiple spanning tree allows you to do is take those 100 VLANs and map them to a spanning tree instance. So instead of having 100 instances of spanning tree, you end up only having 2 instances of spanning tree, and the VLANs then get mapped to those instances, if that makes sense. The VLANs get mapped to those instances. So you're reducing the amount of Bpdu traffic and significantly in that particular case. That's what multiple spanning tree is all about. And we'll see that later on when we get into our multiple spanning tree section. All right. So spanning tree protocol is 802.1d. You can only have one tree. Everybody has to assume the same tree, even if you have 100 VLANs, and it's very slow to converge. PVST Plus, that's Cisco's version of spanning tree, also very slow to converge because it was based on the original version, common spanning tree protocol, but you could at least manipulate spanning tree per VLAN, right? Now, that's great, but it's also going to require a lot more resources because you're now generating Bpdus for each VLAN. Rapid spanning tree 802.1w, very fast to converge, but again, only at one common spanning tree per VLAN, very fast to converge, but one spanning tree topology per VLAN. And then Mstp, like I said, developed by Cisco in conjunction with IEEE. And that's where you create those instances of spanning tree and you map VLANs to the instance. All right. And they break down the details there in the book, but I'm not going to read those. I think I've pretty much covered most of that in our discussion. All right. One thing I did not mention here, Mstp is an IEEE standard inspired by Cisco. And you can have up to 16 instances of a rapid spanning tree topology. So Mstp uses rapid spanning tree as its underlying protocol, but you create the topology per instance, not per VLAN. And you can have up to 16 instances. We'll get more into that a little bit later on when we get into the Mstp section. And we start doing that section later on. The default mode of spanning tree is PVST Plus, which is not good. I mean, it is per VLAN, but it's based on 802.1d. So you'll see in our configuration exercise where we want to run rapid spanning tree, we're going to go ahead and switch to rapid spanning tree by using the global command spanning tree mode rapid. All right. Which of the following options is an IEEE standard that is inspired by earlier Cisco proprietary MISTP, multiple instance spanning tree protocol, that maps multiple VLANs to the same spanning tree instance? That would be MSTP, the multiple spanning tree protocol. All right. All right, guys, welcome to discovery number 4. This discovery is called Tuning STP and Configuring RSTP. In this discovery, there are a couple of loops in this topology, switch 1 to switch 2 to switch 3, and switch 2 to switch 3. So the network has been kind of configured this way for the purposes of going through the exercise, obviously, but switch 1 and switch 2 are supposed to simulate distribution layer switches in this particular topology, and switch 3, would represent our access layer switch. So typically we would have redundant connections to the distribution layer, and that would be the reason why we would want to have to implement spanning tree, because we want to make sure that even though we do have redundancy in the topology, we don't want those loops in our layer 2 network. Spanning tree's already been running on the switches. It's already kind of been, well, it hasn't really been configured. It's just kind of operational, which is the default mode anyway. So the first thing that we're going to do is explore the spanning tree protocol configurations on the switches, and then we're going to tune those configurations by manipulating things like priority, cost, timers, and so on in the spanning tree protocol. We're also going to take a look at the differences between the spanning tree protocol and the rapid spanning tree protocol configurations, and we'll even take a look at some of the convergence times. Now, in this exercise, there are three primary focuses that we're going to focus on. Taking a look at STP and looking at the configurations, tuning STP to get the desired result in the topology and the desired configuration, and then finally configuring rapid spanning tree on each of the switches in our topology. And we're also going to take this opportunity to review some of the concepts that we've covered throughout the lesson and also in future lessons as well, just to make sure that we kind of hit home some of those key points that we discussed during the lecture portion of this series. So the first task that we have is going to be kind of just taking a look at the spanning tree protocol configuration on each of the switches. So we're going to issue the show spanning tree command on all three switches, switch 1, switch 2, and switch 3, and identify presently who the root bridge is. So let's go ahead and start with switch 3 in this case and take a look at the configuration, show spanning tree. And we can see from this particular output, there's a couple of actual things I want to mention here. When you run the command show spanning tree, you're going to see the VLANs listed incrementally because Cisco by default implements a per VLAN spanning tree version of 802.1d. So it says here spanning tree is enabled and the enabled protocol is IEEE. Now that does not mean that we're running the IEEE specification in this particular case. It actually means we're running a variant of the IEEE specification, but which one, right? Well, the default mode is 802.1d. And I always kind of joke with my students and I say, you know what? 802.1d, you know what that means? That means don't use this version of spanning tree because it's really, really slow. It takes a while to converge. Now, we're not actually technically running 802.1d in this case. We're running Cisco's version of 802.1d, which is called PVST Plus, per VLAN Spanning Tree Protocol Plus. Now, the reason that's significant is because the way we handle bridge priorities and the way the bridge ID is identified is going to be different than your traditional 2-byte bridge ID. With a 2-byte priority field and the 6-byte MAC address. What Cisco does is they take that 2-byte priority field and they break it up into two pieces. The higher order 4 bits represent the priority and the lower order 12 bits represent the VLAN. So you'll see here that the priority is listed at 32.768, which happens to be the default for spanning tree. And with the system ID extended field, which is that 12-bit field, we represent the VLAN. So overall, the priority ends up being 32.769. Now, the point of this is to make it somewhat backwards compatible with older versions of spanning tree or other versions of spanning tree that may not be running extended system IDs or per VLAN spanning tree where they might be using a common spanning tree protocol. A couple of other things here. This is broken down into basically 3 sections. The first section is the roots information. The second section is this switch's information. And then the last section is the port interface configurations or operational status, right? So we can see in this case that we're not the root. This switch is the root. We don't know which one that is yet, but I'm guessing it's switch number 1. This is our MAC address. Notice we have the same priority as the root, and the tiebreaker in that case is MAC address, and lowest always wins in spanning tree. Lowest always wins in spanning tree. So 300 is higher than 100, which means that 100 wins in this particular election. Some other things that we see here, the cost to get to the root is 4. The port that I'm using is gig 03 because we start at gig 00, so this is port number 4. We have our Bpdu advertisement timer at 2 seconds, our Bpdu max age timers at 20 seconds, and our forwarding delay, which is typical for listening and learning states, which are the temporary transitionary states between deciding whether or not we're going to be a forwarding port or a discarding port, is going to be 15 seconds each. All right? And we can see the state of each of the interfaces. Now, there's a couple of things I'm going to point out about this, but I'm going to continue on. Let's take a look at switch number 2 in this case and see what we see with switch number 2. Show spanning tree. And we can see, again, switch number 2 is not the root. It does have a 32.768 priority, so it's going to lose the tie to switch number 1. All right? Which means that switch number 1 should be the root for the VLAN. If we did have additional VLANs here, we could easily see which switch is the root for each VLAN. However, I will say this, because we haven't really configured any values, the result would be the same for every VLAN in the topology because we're using MAC addresses as our tiebreaker. So switch 1 is the root bridge. All the bridges as we've seen, or all the switches as we've seen, have the same priority. So in essence, the switch with the lowest MAC address is elected at the root, as the root. All right. The other thing that we can look at is if we take a look at the topology diagram here, we can see if switch 1 is the root bridge, that would be the first step in the spanning tree algorithm. The second step in the spanning tree election process is to determine on all of the non-root bridge switches, which would be switch 2 and switch 3, what is the least cost path to the root. Now gig 03 has a cost of 4. If I were to go this direction over gig 2 or gig 1, that would be a total path cost of 8 because it's a cumulative path cost. Same thing for switch 2. Switch 2 would have a path cost of 4 to get to switch 1 over this link, and it would have a cost of 8 to get over this link. So gig 2 on switch 2 should be a root port, and gig 3 on switch 3 should be a root port. So the only thing remaining is to determine what happens with these two links between these two switches, switch 2 and switch 3. And that's where we have to decide what ports are designated and which ports are non-designated. Now the root is always going to have designated ports because of the way we choose our designated port. In essence, the designated port is the port that's attached to the switch on a single link that has the lowest bridge ID. And of course, the root's never going to lose that election. So between switch 3 and switch 2, we would say that switch 2 in this case would win because it has a lower MAC address. So gig 1 and gig 3 on switch 2 are going to be designated, and switch 3, gig 1 and gig 2 are going to be discarding ports. So let's go ahead and confirm that on switch 2. Shows spent, well, we have the output right here. So gig 02, as suspected, is the root port, and gig 1 and gig 3 are designated ports. All right, now let me point out a couple of other things here because this is really important. The status and the role are significantly different concepts, although they're related to each other. The role of a port really defines its function within the spanning tree topology. Is it a root port? Is it a designated port? Is it a non-designated port? Based on the role, and that of course is based on the election process or the algorithm, the status will be determined. For example, a root port and a designated port would have a final status of forwarding, whereas a non-designated port would have a final status of discarding. So that's important to understand here, and we can see, of course, the port cost. This is the local cost for each of the interfaces, not any kind of cumulative cost to the root or anything like that. It just happens to be what the switch is advertising as the local cost for this particular interface. If I was to go into my GNS3 here, for example, and I start doing a packet capture on this interface, what I'm going to see is I'm going to see those Bpdus coming across the link, and those Bpdus will indicate what the topology looks like in this particular case. So let's wait for this to pop up here, and we'll see what we see. All right, so we're seeing our spanning tree Bpdus. This is from switch 1, switch 1, switch 1, switch 1. So we're seeing all of the spanning tree Bpdus from switch 1, which in this case would make sense because switch 1 is the root. Now if we go and take a look at the spanning tree process, we can see that we're running spanning tree. This is a configuration Bpdu, so we're kind of in the process of making sure that everybody understands what the overall topology looks like. This is a standard 2-second Bpdu. If this was a topology change notification Bpdu, we would see the flag here, topology change flag set to indicate that this is a change. Here's the root's information. The path cost to the root is 0 because I am the root for this VLAN. And then the bridge ID is going to be the same as the root ID in this particular case. Hex 8001 simply indicates the port number. This actually references the number and the port. So if you were to take this, for example, the number and the port, 128.1, and you were to convert that to hexadecimal, which would be essentially 8 bits, right? That would indicate that, that port number, and that's what we're seeing in this particular Wireshark capture. Is this is 8 bits, which represents the 128, the 80, and the 01 represents the port number. So it's a 16-bit field, but it represents each of those 8 bits that are represented in the actual Bpdu. And then here's our timers. So we're not seeing a whole lot of extra information in this output that you would maybe perhaps expect to see, given that this is an actual Wireshark capture. All right, we'll try to take a look at some more of these captures as we continue on here, but so we'll leave that capture running. Let's go back into our config here. All right, so since switch 1 is the root in this case, it has both its connected ports in a designated role, which means it's in a forwarding state. All right, because switch 2 and switch 3 are not the roots, only one port gets elected as the root for each of those two switches. The root port, like I said, is the port with the lowest cost to the root bridge. Because switch 2 has a lower bridge ID than switch 3, all the ports on switch 2 other than the root port are going to be set to designated, and all the switch ports on switch 3 other than the root port are going to be non-designated. Now Cisco, if you look at the output here, actually let's go to a different switch that's going to have some non-designated ports. That's the term we use in the algorithm. But you'll notice here it identifies it as alternate. Now that can be a little confusing because we introduce a new port role within Rapid Spanning Tree called the alternate port role. This is just a term that Cisco's PVST Plus uses for non-designated ports. The block port is known as the alternate port. In Rapid Spanning Tree, it's actually an alternate path to the root. Just happens to be less desirable than the primary path to the root. But in any event, it's still discarding that information. All right. So in our next task, we're going to take a look at how do we tune spanning tree protocol, how do we configure it on the switches, how do we change priorities to manipulate the values. We don't want the network to choose the root bridge by itself. If all the switches had their default spanning tree priorities, which they do in this case, the switch with the lowest MAC address will end up becoming the root bridge. That means the oldest switch will usually have the lowest MAC address, since the lower MAC addresses were factory assigned first. So to manually set the root bridge, we have to manipulate something called the priority, which you guys are aware of because we talked about that in our lesson. In this topology, we do not want access layer switches, like switch 3, to become the root. If switch 3 were to become the root, the link between the two distribution layer switches would get blocked, and the traffic between switch 1 and switch 2 would then have to go through switch 3. Obviously, that's not an optimal choice. We want the distribution or core switches to become the root in our topology. Now, there are two ways that we can actually change the switch priority. We can set the exact value, and that value must be anywhere from 0 to 65,535 in increments of 4,096. So I can come in here and I could say spanning tree VLAN 1 priority, and I can specify a value from 0 to 61,440. It doesn't quite go up to 65,535. I mean, it's a 16-bit field, so mathematically it should, but we have to implement it in increments of 4,096. And that's because if you consider it, the field that was typically used for the priority was a 16-bit field. And when Cisco decided to run outside of a common spanning tree topology and run per VLAN spanning tree, they had to have a way of identifying the VLAN that the Bpdu was associated to. So they split that 16-bit field into two parts. They created a 12-bit field, which is the lower order 12 bits, and that became the VLAN. Now remember, that only goes up to 2048, in the powers of 2 scale. So what they did for the last 4 bits is they started those at 4096, 8192, 16384, and finally 32768, which is why we're limited to only 16 possible values and using that in in increments of 4096. Now the other option is to do a root primary command or root secondary command. All right. Now this is a macro. This allows the switch to kind of, I would say, almost automatically choose which priority it's going to use for the particular configuration. We have to have the correct values. The priority, like I said, can be anywhere from 0 and actually technically 61,440 because we're operating in increments of 4,096. Now the default is 32,768. With per VLAN spanning tree, because we have that extended system ID, which is used for calculating the priority, we reduce the priority field from 16 bits down to 4 bits because, again, 12 of those bits represent the VLAN ID. With a priority of 4 bits, there's only 16 possible combinations. So, for example, an increment value of 15 becomes a priority of value of 61440, meaning that all 4 bits are set essentially, because that's 4,096 times 15. You cannot change the priority from 32,768 in this case to 32,789 or something kind of arbitrary. You have to do it in multiples of 4,096. And that's simply just because of the fact that we only have those 4 bits and they're not numbered from 1, 2, 4, and 8. They're numbered from 4,096 all the way up to 32,768. So the best solution, in my opinion, and most Cisco documentation will concur, is to go ahead and set the priority using the spanning tree VLAN root primary or secondary command, which is just a macro that's going to lower the switch priority number one time only when you execute the command in order for it to become the root bridge. To configure the switch to become the root bridge for a particular VLAN, we do that with that particular VLAN. We can use the secondary keyword that you see here to configure the secondary root bridge if for some reason the primary root bridge fails. We don't want that next switch to be that oldest access layer switch to become the root in the failover event. All right. Now, a couple of things about this macro real quick. If the current priority of the switch is more, not equal to, but more than 24,576, the local switch is going to set its priority to 24,576, which happens to be 8,192 below 32,768. If the root bridge has a priority lower, the current root bridge, before I execute the command, lower than 24,576, then the local switch sets its priority to 4,096 less than that value. All right, until we can finally not go any lower once we get to 0. When we set up the secondary, and this is really important because you can run into a situation with this, we set the priority to 28,672. There's actually technically no way for a switch to figure out what the second best priority is in the network because we're basing it on what we're getting from the root, those Bpdus that we're getting from the root. So setting the priority to 28,672 is kind of just a best guess, if you will. So you may have to manually configure that. All right. Now, typically we would have like one distribution switch as the primary, another distribution switch as the secondary for a particular VLAN, and then maybe it's the opposite in the other VLANs and so on. If the priority of the root is already 0, when we execute the primary command, it's not going to result in any change. Basically, the command's going to fail because it can't make the local switch priority 4,096 lower than whatever the root is. All right. You would think that maybe perhaps it would set it to 0 and say, okay, well, let's let the MAC address be the tiebreaker. No, it says, you know what? There's already a switch with a low priority in here, the lowest it can go, so we're not going to try to attempt to become the root. So let's go ahead and in this case, we're going to go into switch 2, and we're now going to make switch 2 the root for VLAN 1. Oops. All right, so config T, spanning tree, VLAN 1 root primary. All right. Now, if I do a show spanning tree, I should see that this bridge is now the root for VLAN 1, and sure enough, it set the priority to 24,576. Okay, so that's exactly what we would expect to see. The change takes effect immediately, And if we start to go investigate the other switches, if I look at the topology here, where's my topology? There it is. Switch 2 is now the root, which means that these are now designated ports. This is a root port, and then we've got some sort of tiebreaker here. Okay, whether gig 01 on switch 1 should actually be designated. So let's confirm switch 1 first. Show spanning tree. And sure enough, gig 00 is the root and gig 01 is designated. Now what about switch 3? If we look at the topology diagram, figuring out the root is a bit of a challenge. Certainly, we already know what the status of this port is. Gig 03 is going to be non-designated or alternate. But what do we do about these two ports? All right, gig 2 and gig 1. Well, the election of, there's never a tie in spanning tree. There's always some sort of tiebreaker, and that tiebreaker is always lowest value. The question in this case is, what is that lowest value that we're going to consider? Well, we have switch 2 here, which has gig 1 and gig 3. Switch 2 is advertising to switch 3 the port priority and the port number for those interfaces. Switch 3 is going to choose the path, which is going to become the root port, that is connected to the port that's sending out the lowest values, right? So in this case, gig 01 on switch 3 should be the root, which means gig 02 and gig 03 should be non-designated. So let's go to switch 3 and let's do a show spanning tree. And we see that in fact gig 01 is the root and gig 02 and gig 03 are alternate, which is non-designated. So everything is happening the way that we expect it to happen. But there's a lot of confusion about this idea of this tiebreaker when we have two paths that have the same cost to the same neighboring switch. And the tiebreaker is always, what is the neighbor advertising to me for priority and port number? Now I can influence this election process. I can change those values on switch 2 to advertise some different values. I could change the cost if I wanted to on gig 02 to make that path a little bit more preferred. We'll probably take a look at that in a little bit here. But the point is that there's always a tiebreaker, okay? So for switch 3's perspective, for the port role determination, by the way, let's see what's happening with our Bpdus here. And sure enough, we can see that the Bpdus are now being sent by switch 2. Right? Switch 2 indicating that switch 2 is now the root for the topology. All right? So for port role determination, the cost is always going to be used, right? Especially for root port role determination. If all the ports have the same cost, then there has to be a tiebreaker. And that's what we see here between switch 3 and switch 2. Well, the first tiebreaker is always going to be cost, right? The lower the cost, well, in this case, that doesn't matter because then it wouldn't be a tie. If one cost was lower than the other, we wouldn't have a tie. But the thing that we look at is the sender's port ID, which breaks that particular tie. So to control the active port selection, we can change the cost of the interface. Either make one port cost more or make one port cost less, or we can actually change the sender's port ID. Now the port ID is a combination of two things. It's a combination of priority and number. The number is tied to hardware. That's not a value that you can modify. But the number, the priority, is a value that you can modify. All right? Now if I was to change the cost of an interface, I would come into interface gig 02, for example, and I could say spanning tree VLAN 1 and simply put in a cost value. And you'll notice here I have an option of a cost of 1 to whatever that big, large 2 number is, right? That happens to do with kind of more of a modern approach to spanning tree metric for path cost because of the bandwidths that we see in modern networks today, all right? Now, it's typically that cost value would be anywhere from 1 to 65,535. This is a newer model switch, so it's going to support kind of the newer cost values that are available for things like multiple spanning tree and just in general, just running the larger cost values because we're going to have possibly 10 gig links or 40 gig links and so on. Like I said, the port ID consists of the port priority and the port number. As the port number is fixed, Well, it's tied to the hardware, right? You can only change the port ID information or influence the port ID selection process by the port priority. We can modify the port priority by simply using the spanning tree VLAN1 port priority command. And that number can be anywhere from 0 to 255. The default is 128, and the lowest always wins. So in this particular case, let me go back to the topology real quick. If I'm looking at this switch here, gig 01 and gig 02 on switch 3 have the same path cost, which is 4 to the root. Gig 01 on switch 3 is forwarding because the sender's port ID, which is 128.2 on switch 2, is lower than that of the sender port ID on the other interface, which is 128.4, right? So one way we can make switch 3 gig 02 as the forwarding port is to lower the cost on that port to something lower than 4. So let's say, for example, I'm already in gig 02, and I'm just going to change that value to 3. So if I do a show spanning tree, I should see now, we're going to go through our listening and learning states because we triggered a topology change. And I actually should see a topology change Bpdu here. Let's see, yep, topology change notification, indicating that the topology changed. So that TCN looks pretty much the same as it would normally, but it gives us a little bit less information, saying that, hey, we're triggering a change, and then we would see some information about what that topology change is. So here's the actual Bpdu that acknowledges that topology change is taking place. All right, and it's really just a matter of this port, number 3, on switch, let's see, the advertising switch in this case is switch 2. It depends on where we're capturing this information, but we're seeing that topology change notification is occurring. Now keep in mind that is happening based on standard spanning tree processes, right? Where the topology change triggers a topology change notification towards the root, and then the root has to send a TCA, a topology change acknowledgement, and then the root will process and propagate that information to the rest of the switches in the topology. Okay? We should be converged at this point. It's been more than 30 seconds, so if I come back in here and I take a look, I can see gig 02 as the root port because it has a lower overall path cost to the root. All right? So that's one way of doing this. The other option that we have is to change the priority. So let's say, for example, I wanted to not influence the path selection based on that. I wanted to influence the path selection based on changing the priority on switch 2. So this case, I'm going to go into gig 03, and I'm going to set that value. Interface gig 03, spanning tree VLAN 1, port priority. And you can see it goes from 0 to 224. It actually technically goes all the way up to 255, but we're also incrementing this in blocks of 32. And 224 plus 32 is 256, which we can't actually get to, right? So we know that the priority is 128. I could make it 64, for example. And the same thing would occur in this case. We'd still go through our listening and learning states, but again, gig 02 becomes the root port in this particular case. All right, because it's getting that information from the neighboring switch. The costs are the same, but it's not this port priority and number that makes a difference, it's what's on switch 2. So I'm going to go ahead and set this back, and we're going to go ahead and put the cost here. And let's play around with some other options as well. Now, keep in mind that by modifying this cost on port 3 here, we are obviously changing how, oops, sorry, it was gig 02. We're changing how, let me see, I thought it was gig 02 that we modified here. Show spanning tree. I might have removed it. I'm going to put it back in. Yeah, let's go back into interface gig 02 and spanning tree VLAN 1 cost 3. All right. Now, by modifying this cost on gig 02, this is now going to be the path. Now, the question is that going to affect the root port on switch 1? And in this case, it wouldn't, right? Because this path cost is 4, this path cost is 4. So even if I made this a 0, which I can't really do, or even if I could potentially make it a negative number, I'd have to make it -5 just to make these paths not be considered equal. Obviously, that's not going to be something that's going to be doable in this particular case. But you do have to consider what the specific impacts are of modifying different path costs and port values and so on, because it may not affect just your switch. It may affect other switches within the topology. So just to recap here, switch 2 is the root. The path cost for the top path is 4. The path, this port here, well, actually, let's consider this, right? Is this a designated port or is it a blocking port? And switch 1 does have a better priority than the other switches, so technically that should be in essence a designated port on that particular switch. And it depends, right? It depends on if we modify priority values and so on between the switches. If we did, say, for example, root secondary for that switch, it would ensure that that port is going to be a designated port. All right? So it just depends on how you manipulate these particular values. So what we're going to do on switch 3 is we're going to turn on some debugging events, and we want to take a look at the convergence process and see how long it takes for us to converge here. So we're going to go into switch 3 in this case. We're going to go ahead and do a debug. And the debug we're going to do in this case is just debug spanning tree events. And there we go. And we're going to go ahead and go into interface gig 02. And we're going to shut that interface down. So we should see in this case some specific spanning tree events taking place. We can see the new root port becomes gig 01. We go into kind of a listening state. We generate a topology change notification trap based on the gig 02 going down. And then we start to move into what we call the learning state. Notice here from the listening state to the learning state, we had, let's see, 652.29 and then 652.44, which is give or take about 15 seconds or so. Pretty close to right on 15 seconds as we move from those to those different states. So we're seeing that we're kind of transitioning through these different states, and this has to do with all those timers, right? There are 3 different timers to ensure proper loop-free convergence. The hello time is basically just the time between each Bpdu on a port. Basically, it's 2 seconds by default. The forwarding delay timer is the time that's spent in the listening and learning states, which is equal to 15 seconds by default. And then finally, the max age timer, which controls the maximum length of time that passes before a bridge port saves its configuration Bpdu information, which is 20 seconds by default. So the transition time for when a port state changes could take anywhere from 30 to 50 seconds, depending on the topology change itself. Now we could adjust the timers. We can tune the hello timer from anywhere from 1 to 10 seconds, the forwarding delay anywhere from 4 and 30 seconds, the maximum age anywhere from 6 to 40 seconds. However, the timer values really should not be changed. When we're changing the timers, we need to apply those changes also only on the root, and then the root bridge will actually propagate those timer values to the other switches in the topology. But, you know, there's a better solution than that, right? The better solution is just to go ahead and use rapid spanning tree protocol. All right, now I could go into the command. I could say spanning tree, VLAN, whatever, hello time, forward time, max age time, if I wanted to. But that's not what we're going to do in this case. In this case, we're going to go ahead and take a look at what it is to configure rapid spanning tree protocol. So let's go ahead and do a no shut and bring that port back up. If we go back and verify our topology, we'll see our topology is back to where it should be. All the port roles and are again the same way as they were before we shut down that interface. Switch 2 is still the root in this topology, by the way. So it takes about 30 seconds, again, like I said, for a spanning tree to make all the ports into either a forwarding state or a blocking state. So let's go ahead and turn off our debug. Do undebug all. And in our next task, what we're going to take a look at is how do we configure rapid spanning tree protocol. Now, if we did a comparison, right, side-by-side comparison between RSTP and STP, RSTP port states correspond basically to the three basic operations of a switch port. Is it discarding, is it learning, or is it forwarding? They actually got rid of the listening state in rapid spanning tree, and the alternate or non-designated port role has just been simply renamed to discarding. All right, the listening and blocking states also get replaced with discarding as well, even though we don't really have a listening state. So in a stable topology, rapid spanning tree ensures that every root port and designated ports transit to forwarding, while all alternate ports and backup ports are always in the discarding state. All right, which is what we would expect to see for those particular ports. Now the backup port you probably won't see too much. There's two new port roles that are defined in rapid spanning tree. The alternate port, not to be confused with what they call basically the non-designated port role, and the backup port. The backup port provides kind of a redundant but less desirable connection to a segment where a root port already exists, which means that it would have to be another path through a same neighboring device, typically a hub, in order for that to happen. It has to be the same neighboring switch, and it has to be on the same segment, which is basically meaning a hub. All right? So you're more often going to see the alternate port, which is basically another path through another switch, a point-to-point link that has the second best path cost to the root. Now, in regular spanning tree, the root port is a forwarding port. In rapid spanning tree, the root port is a forwarding port. In regular spanning tree, the designated port is forwarding. And in rapid spanning tree, the designated port is forwarding. In regular spanning tree, the non-designated port is blocking. And in rapid spanning tree, the non-designated port is discarding. In regular spanning tree, disabled means we're just simply not running spanning tree, and that would be the same as rapid spanning tree, except we would call that discarding. And finally, the transitionary roles. In regular spanning tree, we have listening and learning, and in rapid spanning tree, we only have learning. So we're already cutting the time down by 15 seconds. All right, so what is a discarding port state? What does that represent in rapid spanning tree? This state is seen in stable, active topologies, and whenever we're doing some sort of topology synchronization or when there's a change. The discarding state prevents the forwarding of data frames, which breaks that continuity, if you will, of the layer 2 loop. That's a really, really important concept. That's the whole point, right, of a non-designated, or in this case a discarding role, is to break that loop. The learning state can be seen in both stable, active topologies and also during synchronization and changes. The learning state accepts data frames to allow us to populate the MAC table, but it limits the flooding of unknown unicast frames. So in other words, we're not going to be forwarding traffic with a learning port, but we will be updating the CAM table. And finally, the forwarding state is the only, we're only going to see forwarding in an active stable topology, where the port has determined that the algorithm itself has determined the port's not going to cause a loop, and the forwarding state just operates like a normal forwarding port. So what we're going to do is we're going to enable rapid spanning tree on all of these switches here. Let me make sure I'm good to go. And we'll go back to that one. All right. Config T spanning tree mode rapid. And same with switch 3. Config T spanning tree mode rapid. And finally switch 1. Now, this mode of spanning tree is compatible with the other versions of spanning tree. In fact, if you look at the Bpdus, they look pretty much the same. Let's see if we're actually capturing any Bpdus anymore in this case. Looks like we are. Yep, we are still capturing Bpdus. Let me make sure. Yes, we are. So if I now go into this Bpdu, I can see that the protocol ID is protocol number 2, which is rapid spanning tree. Now we do see quite a few more flags here, right? Is the port forwarding? Is it learning? Learning is a stable state, right? Learning is not always just a transitionary state because all forwarding ports are also learning, right? This is a designated port, and we can tell which port it is based on the port identifier and the bridge ID, so we know exactly where that port is in the topology. But you can see here, as far as outside of the flags that we have here, there really isn't a whole lot of change to the overall format of a rapid spanning tree Bpdu, which is why rapid spanning tree can work very well with 802.1d or PVST+. All right, now if all switches in the network except for one are running RSTP, the interfaces that go to the legacy STP switch will automatically fall back to non-rapid mode. And that means they'll fall back to PVST plus in this case. All right, now if we go into our switches and we just simply do a show spanning tree, we can see that we are running the rapid spanning tree protocol. And I can confirm that on each of the switches here. Rapid spanning tree protocol there, do show spanning tree, rapid spanning tree protocol there. So we know that it's now enabled on all of the switches. Now, a couple of things that are going to happen here, if I do a show spanning tree summary, one of the a couple of interesting things that are going to happen are these two features are going to be enabled by default, uplink fast and backbone fast. All right. Some other features would still have to be configured manually, but uplink fast and backbone fast are going to be enabled by default. So we typically don't really talk about those two configuration options in spanning tree these days. All right, but we do talk about some of the other toolkit options. Now for rapid spanning tree, well, let's review real quick what happens in regular spanning tree whenever there's a topology change notification. So let's say switch 2 is the root and gig 3 goes down on switch 3. That's going to generate a topology change notification, which gets sent from switch 3 to the root. The root then sends a topology change acknowledgement, or TCA, back to switch 3, and then the root will then in turn propagate that change information to the other switches in the topology. Now with three switches, that's not a big deal, but you start to get into potentially 10, 20, 30, 40 switches, it can be a very, very slow process. In rapid spanning tree, the topology change occurs only when a non-edge port transitions to the forwarding state. So a loss of connectivity in this case is not actually considered a topology change, which is completely different from regular spanning tree. All right, so first of all, we have non-edge ports and we have edge ports that are defined. A non-edge port changes its state to a forwarding state. All of the switches in this case can send out Bpdus for that topology change, not just the root bridge. So a switch is going to announce a topology change by sending out a Bpdu with the topology change bit set out from all of its non-edge designated ports. That means that all the neighbors get informed about the topology change so they can correct their bridging tables immediately without having to wait for that information to be propagated to the root and then have that information propagated back to the rest of the switches. All right. So if a switch sends out a Bpdu out of all of its ports after it detects a failure, Then the neighboring switches, they're going to send the BPDU to their neighbors, and they'll send it out of every port except for, of course, where they receive the BPDU and so on. When a switch receives a BPDU with the TC bit set from the neighbor, the first thing it does is it clears its MAC address table completely on all of its ports except the one that receives the topology change notification. The switch also then sends a BPDU up to the neighbors, or to its neighbors, with a TC bit set on all of its designated ports and the root ports. So we don't have a specific, in rapid spanning tree, we don't have a specific topology change notification BPDU unless there's some sort of legacy bridge in our topology. Okay? So in essence, what does that mean from a reconvergence standpoint? With rapid spanning tree, the TC propagation is now just a one-step process. In fact, the initiator of the topology change floods this information throughout the entire network, whereas with PVST Plus or 802.1d, only the root was able to do that before. So it's much, much faster than the equivalent 802.1 protocol, 802.1d protocol or PVST Plus. There's no need for us to wait for the root bridge to be notified and then maintain the topology state table for the whole network for that max age timer plus the forwarding delay timer in seconds. It's actually just a few seconds and a couple of hello times the entries in the CAM table of the entire network get flushed, and it results in much potentially clearly much faster convergence process. Now there could be some temporary flooding, but it does clear out potentially stale information that prevents rapid connectivity restitution when we're trying to do our communication. So why does rapid spanning tree protocol not consider a link failure a topology change? Right? Loss of connectivity does not provide any new paths in the topology. If a switch loses a link to a downstream switch, the downstream switch either has an alternate path to the root or it doesn't, right? And it would have already selected that as part of the process. If the downstream switch has no alternate path, we don't have to take any action to improve convergence because, well, that switch is just disconnected, right? If the downstream switch has an alternate path, the downstream switch will unblock it, and then it's going to generate its own BPDU with that topology change bit set. So just like with spanning tree, PortFast enabled ports are not going to create topology changes, and that's going to reduce the overall amount of time that messages get flooded and so on. All right. Remember, PortFast enabled ports do not have associated MAC addresses that get flushed if a topology change message is actually received on those particular ports. All right, so let's go ahead and do our debug again on switch 3. All right, and we're going to go back into interface gig 02, and we're going to shut that interface down. All right. So you can see here that we didn't go through a listening state. We didn't go through a learning state. How much time did it actually take us to converge? Well, actually it was pretty quick, right? The port went down at 708.06.292. Gig 1 became the root port at 708.06.293, right? And there's some other messages that are being sent, but the bottom line is that the convergence time was nearly instantaneous, right? The entire convergence time basically happens at the speed of however long it takes to transmit a BPDU, which is typically less than 1 second. Because remember, these are triggered updates, right? So we can go back now and verify the state of all the interfaces, and we wouldn't see the listening and learning in this case. Everything would be kind of operating normally, right? We would have already converged. So we talked about this briefly, right? What are the different rapid spanning tree protocol link types? The link types provide us a way for categorizing the ports that are participating in spanning tree. All right, now a link type can actually be predetermined, and it can actually predetermine the active role that the port plays as it stands by for some sort of immediate transition to a forwarding state. All right. So there are, in essence, two different types of links, and I did mention this briefly, but I'm going to mention it one more time. A point-to-point link is any link operating in full duplex mode, and it's assumed that that port is going to be connected to a single switch or a single device at the other end of the link. And then we have our shared links, which typically operate in half duplex mode, and this assumes that the port is connected to some sort of shared media where you might have multiple ports that exist. All right. And we know that in our case we're running point-to-point links. Now this link type is automatically determined, but it can be overwritten if you want to explicitly overwrite that configuration. We also have something called an edge port in rapid spanning tree. An edge port is a switch port that's never intended to be connected to another switch device. Edge port's basically the same as a point-to-point link. Those ports are going to be candidates for rapid transition to a forwarding state because they're not, even if they come up and operational, they're not going to cause a loop in the topology. Before the link type parameter can be considered for some quick port transition, we have to determine the port role. All right. Now there is a user configured value and an operational value for the edge port state. The Cisco implementation maintains that PortFast keywords be used on those edge port configurations, making the overall transition to rapid spanning tree simpler. And you can do that by doing the spanning tree PortFast default in global mode or exclusively enabling it on the interface itself. All right. Remember, root ports do not use the link type parameter. Root ports are able to make the rapid transition to the forwarding state when the port is in the synchronization process. All right. Alternate and backup ports do not use the link type parameter either, but they're basically the secondary component or the secondary path to the root in that particular case. So it's really the designated ports that make the most use out of the link type parameter, and rapid transition to the forwarding state for a designated port only occurs if the link type parameter indicates that it's a point-to-point link. So we can actually go into a switch port. Let's say on switch 1, we'll do this on gig 01, and then on switch 3 we'll do this on gig 03. So let me go into switch 1. Let me turn off this debug. And let's go into gig 01 here. And let me say spanning tree link type point-to-point, and then same thing on switch 3. And I believe that's gig 03. Let me check real quick. Yep. And spanning tree link type point-to-point. Okay, so we can statically configure this value. And if I do a show spanning tree on switch 1, I don't really see much of a difference, right? I see that it is a point-to-point link. Now, I may decide that I'm going to override this behavior. For some reason, perhaps, maybe the port is showing up as a shared port. It would just have an SHR there instead of a P2P. And I want to make sure that the switch knows that this is actually a point-to-point link, so I can actually do that. All right. Obviously, there's a whole bunch more to talk about with spanning tree, the spanning tree toolkit, and we'll talk about multiple spanning tree in one of our next discoveries. But that concludes this lesson. And now we're going to get back into our lecture and get into some more discussion about spanning trees. So we'll see you guys in the next discovery. So going into the next section here, multiple spanning tree, and you guys are going to be doing an exercise here shortly on this. Multiple spanning tree is a way for us to reduce the total number of actual spanning tree instances running in our topology. Because if you think about it, if you're using a standard core distribution access layer design, and you've got your access layer switches redundantly connected to the distribution layer, most likely you're only going to have 2 distribution layer switches. You're not going to have more than 2 distribution layer switches, which means that one switch can act as the root for one set of VLANs, and the other distribution switch can act as the root for the other set of VLANs, and you're good to go, right? You shouldn't have any problem And there's no need to run, if you have 100 VLANs, 100 instances of spanning tree, because ultimately you're only going to have 2 different topologies. So what multiple spanning tree allows us to do is group VLANs together into an instance to reduce those CPU load and to, in essence, make spanning tree operate more efficiently. So in order to do this, in order to get multiple spanning tree to work correctly, we have to set up the multiple spanning tree domain. All right, now it says here, imagine an example where the goal would be to achieve load distribution with VLANs 1 through 500 using one path and VLANs 501 to 1000 using another path. You could certainly do that in regular rapid spanning tree by setting the priority to root primary for VLANs 1 to 500 and root secondary, a root primary for VLANs 501 to 1000 on the other distribution layer switch. But that still creates 1,000 instances of spanning tree. When really I only have 2 topologies, why can't I just go ahead and create 2 instances of spanning tree and then associate those VLANs to the instance? And that's how multiple spanning tree basically works. You say, I'm going to create instance 1, and VLANs 1 through 500 go into instance 1. I'm going to create instance 2, and VLANs 501 to 1000 go into VLAN instance 2, not VLAN 2, but instance 2. We always will have an instance 0 as well, because there are other VLANs that may potentially exist that weren't assigned to an instance, and there always has to be at least one instance that they're assigned to. But you can understand the benefit, right? It's very clear what the benefit is in this particular case. You're only running 2 instances or possibly 3 instances of spanning tree as opposed to 1,000. And you're still achieving the same per VLAN goal. You're still technically achieving the same load sharing per VLAN goal of mixing which VLANs go to which distribution layer switch. So even though MST uses rapid spanning tree 802.1W, certainly it's going to be backwards compatible with 802.1D because we used the same basic logic for determining the root and root ports and designated ports and so on. We use the same Bpdu format, but obviously MST is going to converge much, much faster because it's based on rapid spanning tree, and also we're using less CPU cycles and less memory to process the information. All right, so MST allows you to build multiple spanning trees over trunks by grouping the VLANs together, associating them with an instance. That's what we call that group, is an MST instance. And then the topologies get built per instance, not per VLAN. All right, so we still have the ability to control spanning tree on a per VLAN basis by establishing the forwarding path for a particular VLAN based on its VLAN to MST mapping. It's VLAN to MST instance. All right. There are a couple of configuration things that have to take place in order for this to work. And typically, if you're going to run MST, you're going to run it through your entire enterprise. You're not going to implement it individually on a couple of switches because you lose a lot of the benefit of multiple spanning tree when you kind of mix and match the configuration options. Now, I don't know if they get into this in too much detail, but with multiple spanning tree, there's an IST, and then there are MSTs. There are instances of that we create, and then there's a kind of a global IST. We actually do not generate Bpdus per instance in this case. We generate one set of Bpdus which contain the instance information. And based on that, we decide what switch is going to be the root for an instance and which switches are not going to be the root for a particular instance. So that being said, there are some issues that you can run into since we're not doing a one-to-one mapping. As number 1 states here, we see that we have VLANs that are being pruned off of the trunk links. the pruning process is not necessarily going to be consistent with the MST configuration. Maybe because the Bpdu carries all of the information for all of the VLANs, VLAN 10 and VLAN 20 might be assigned to the same instance, but we went in and manually pruned VLAN 10 off a particular link, then we're going to see issues with VLAN 10 traffic being passed over that particular link. All right, so because we have 10 and 20 mapped to instance 1, but we filtered 10 off of this link, that's going to be an issue because we're, again, not running spanning tree per VLAN, we're running spanning tree per instance in this case. So it says here, the figure shows a network where VLANs are manually pruned on the trunk links. Because pruning is not consistent, VLAN 10 traffic would be blocked between switch 1 and switch 2. You would have the same problem if you were to configure one of the two links as an access port. For example, if you were to have one link as an access port in VLAN 10, the other link as an access port in VLAN 20, as the second figure, say, with the diagram that you see on the screen here, these two access VLANs would use the same spanning tree instance. But the instance is only going to be active on one of those links. So again, it's the benefit of running multiple spanning tree is that you're able to control spanning tree per instance, but you have to keep that in mind when you're doing things like pruning VLANs off of a trunk link, because typically you would match the pruning to whatever the instance configuration has. All right. Now, I did mention that IST exists versus MST. IST, the initial spanning tree component, is the instance that allows us to propagate all of the VLAN information. We're not going to be generating Bpdus for each instance. So we see switch 1 and switch 2 are connected. This is based on the diagram that we just looked at. Switch 1 and switch 2 are connected with access ports in different VLANs. VLAN 10 and 20 get mapped to those instances. And based on the way that the IST information is propagated. And unfortunately, the book doesn't go into it in near as much detail as the CCNP switch course did. But I think you guys get the general idea, right? The issue is explained by the fact that the MST information is conveyed only with one Bpdu, the IST Bpdu. Doesn't matter how many VLANs are part of the internal instances. We do not send individual Bpdus for each instance. I'm not even talking about VLANs. I'm talking about the instances themselves. The IST Bpdu contains all of the instance information. In fact, let me see if I can't pull that up. So what I've done is I've pulled up a capture of a multiple spanning tree, and you can see it looks pretty similar to what we saw with the standard Bpdu, right? It's a spanning tree protocol, hex 0, but it is multiple spanning tree protocol version, which is a Bpdu type 3, I guess, in essence. It is utilizing rapid spanning tree. We have some different flags here. Looks a lot different than our standard 802.1d spanning tree, but this looks just like it would look if it was a rapid spanning tree. Is the port forwarding? Are we in a learning state? What's the port role? And we have some 8 bits here that allow us to identify the port role. Actually, we only use a couple of bits for that. There's only 4 port roles, right? Root port, designated port, non-designated port, and disabled. Same information with regard to the root. This switch happens to be the root in this case. But notice we don't see anything about instances here. We don't see, this is the IST, by the way, that I was talking about being captured. We don't see anything about instances here because guess what? It's down in the MST extension field. and it identifies, in essence, what the MST information looks like. It's kind of interesting in that it doesn't give us the specific information. In other words, it tells us the CIST information, which is my information. It tells me the region's root information, and we see, you know, kind of what's happening with the MST negotiation in that region. But you notice I don't see really anything about the mappings of VLANs to instances and so on. And that is because we use a digest to confirm that configuration. When you're setting up multiple spanning tree, every single bridge in the topology has to have the exact same configuration. The same region name, the same region version, the same instance, VLAN to instance mappings, everything has to be identical. Because a digest, a message digest, a hash is generated based on that configuration. And if my hash doesn't match your hash, then we don't have a common MST configuration, which means that we're not going to be able to communicate to each other. So it's a little bit different, not quite what you would expect to see in the Bpdu, but the idea, though, here is that this is the only Bpdu that's being sent, which is going to allow us to identify what the topology is going to look like and so on. All right. So we get the Bpdus. It's just something to keep in mind. If you're doing special things like pruning and whatnot, you have to make sure that you're not pruning off VLANs that normally would pass over that particular link based on the overall election process. All right. Which type of port should be configured between switches when we're using MST? Trunk with no pruning, trunk with pruning for unused VLANs, access port with a voice domain, trunk with no pruning. I would say if you're going to be using MST, avoid using pruning altogether. You're not saving much by pruning anyway, and you might have some sort of STIG or some sort of security requirement to prune. Well, in that case, you're just going to run rapid spanning tree so that you can do the pruning appropriately. Which two of the following options are benefits of MST? Reduces the CPU load for sure. It doesn't provide for more active paths because we're still getting rid of all the redundant paths. It's certainly not easier to configure than regular spanning tree because we have to set up the instances, which you guys are going to do in a minute here. There's additional configuration that needs to take place, so the only other option would be faster convergence time. And I would say, yes, that's true, faster convergence time, because we are using rapid spanning tree, not regular spanning tree in this particular case. Okay? All right, folks, welcome back. We are now going to go into discovery number 5, configuring multiple spanning tree protocol. Now, in this particular discovery, we're going to learn how to configure and verify MST as a kind of a modern approach to spanning tree topology design. The diagram that we see here represents kind of the beginning of this lab, although the physical architecture is not going to change. All 3 switches in this particular case are configured with PVST+, which is the Cisco variant of 802.1d. We have 5 VLANs, but 4 user-created VLANs, VLAN 2, 3, 4, and 5. Switch 1 is presently configured as the root bridge for VLANs 2 and 3, and switch 2 is configured as a root for VLANs 4 and 5. This configuration distributes that forwarding traffic between the particular switches and the uplinks, which is a typical design, right? You don't want one switch to act as the root for all of the VLANs because that means all of my access layer, which is what switch 3 is, to my distribution layer traffic load goes over a single link. Now what I want to do is I want to go ahead and open up a Wireshark capture here. We'll let this Wireshark capture run for the duration of what we're going to be discussing here. But the point of taking a look at this Wireshark capture is to just simply see how much Bpdu traffic is being generated for these 4 VLANs. Remember, we have 4 instances of spanning tree running, minus VLAN 1, of course. 4 instances of spanning tree running for each of these VLANs, and we can see there's quite a bit of spanning tree traffic. Both switch 2 and switch 1 are generating these Bpdus every couple of seconds for each of these VLANs. So these VLANs are independent of each other, and they're being managed independently with separate Bpdus for each of those VLANs. We can see quite a bit of traffic. It looks like about every half a second or so we're generating some sort of Bpdu that's being flooded through the network. So we know that based on our topology here that we have really just a basic kind of standard distribution layer switch, access layer switch configuration. And typically speaking, even if I had 100 VLANs, switch 1 would be the root for some of those VLANs, and switch 2 would likely be the root for some of those other VLANs. So we don't really need to have 4 or 5 or 10 or 50 different instances of spanning tree running per VLAN. What we would do is we would basically configure multiple spanning tree to create instances of what we would consider kind of like a common spanning tree topology for the VLANs that are associated to those particular instances. So in this lab exercise, we're going to configure MST. We're going to take a look at the port priority and also path cost and see how that's kind of affected in the multiple spanning tree configuration as opposed to what we saw traditionally when we were configuring regular spanning tree or PVST plus or even rapid spanning tree. Now, the first task is to configure the MST regions. An MST region consists of 3 basic things. Number 1, the name. Number 2, the revision number. And then finally, the VLAN association table. If you recall, Mstp differs from all the other spanning tree implementations in that it combines some, maybe not all, but some VLANs into a logical spanning tree instance. Now the difference raises the problem, right? How do we determine which VLAN gets associated to which instance? More specifically, this means that tagging Bpdus so that any receiving devices can actually identify those instances and the VLANs that are applied to them. So that's a really important concept. In the case of 802.1d, the issue is kind of irrelevant because all instances are mapped to a unique common spanning tree, right? And PVST plus, different VLANs carry the different Bpdus for their respective instances. But again, we have one Bpdu per VLAN based on whatever the VLAN tagging information is. All right? So to provide this logical assignment of VLAN to spanning trees, each switch that's running MSTP in the network, in this case 3 of our switches, have a single MSTP configuration that consists of 3 different attributes. An alphanumeric configuration name, which is 32 bytes long, a configuration revision number, which is 2 bytes long, and a 4096 element table, a 4096-bit element table that associates each of the potential 4096 VLANs, not 4096 bits, but we need to be able to associate those 4096 VLANs to a particular instance. So that's the VLAN to instance mapping that I was referring to before. Now, to ensure consistent VLAN to instance mappings, it's imperative that the protocol be able to identify the boundaries of the specific regions exactly. So the characteristics of those regions are going to be included in the Bpdus. The exact VLAN to instance mapping, that's not going to get propagated in the Bpdu. And we'll take a look at what those Bpdus look like in Wireshark as we continue to do these captures and we start to make our configuration changes in the topology. All right, we don't propagate the VLAN to instance mapping in the Bpdu because the switches need to know only whether they are in the same region as a particular neighbor. For that reason, only a digest of the VLAN to instance mapping table gets sent along with the revision number and the revision name. So once a switch receives a Bpdu, it extracts that digest, which is basically a mathematical calculation or a hash derived from the VLAN to instance mapping table through this hashing process, and it compares it with its own computed digest. Now, if the digests differ...
Sorry, I'm not sure.
That was my Alexa there talking to me. All right, if those digests differ, then that means that the mappings must be different, right? And I'll explain a little bit more about how this works, especially when we see it in the discussion of, actually when we take a look at specifically the Wireshark capture, I'll show you that digest and what we're referencing there. So the port on which, where the Bpdu was received becomes essentially the boundary of the region. And this is stuff that we talked about in the lecture portion of the lesson as well. So in generic terms, like kind of just standard generic terms, a port is at the boundary of the region if the designated bridge on that segment is in a different region, meaning that it has completely different configuration, or it might be receiving some sort of legacy Bpdus, maybe an 802.1d Bpdu and so on. All right, now the configuration revision number, I've always kind of thought that this is a little bit of a strange concept, because typically when we think of configuration revision numbers, we tend to think of those numbers as something that gets dynamically incremented as changes occur, or as, you know, like in VTP, the database revision number and so on. But in this case, the configuration revision number is simply a static value that you configure as an administrator. And as you make changes to the MST configuration, you would basically just update that configuration revision number manually just to reflect that particular change. It doesn't automatically increase each time you make changes to the MST region. So I guess the bottom line is if you do make a change to MST or the MST configuration, typically that would be a VLAN to instance mapping change. Make sure you increase that revision number by 1, even though it doesn't really matter, right? Ultimately, it matters that they match between the peers, but it doesn't really matter ultimately what that revision number is. So let's do a little investigation just to confirm what we've got here. Make sure we have a clean config. So we've got our VLANs 1 through 5. We've got a couple of ports that are presently active in VLAN 1. So VLAN 2, 3, 4, and 5 are most likely being pruned off. We just have some trunks configured between here. We don't really have any active ports in the VLANs, but if I do a show spanning tree, I should see that VLAN 2, this bridge is the root for VLAN 2. This bridge is the root for VLAN 3, but it should not be the root for VLAN 4 and 5. And sure enough, switch 2, which has a MAC address of 200, is the root for VLAN 4 and 5. And then I can also confirm here on this switch, show VLAN, and also show spanning tree, that this particular switch is the root for, not the root for VLAN 2, switch 1 is, not the root for VLAN 3, switch 1 is, but it is the root for VLAN 2, VLAN 4 and VLAN 5. All right, so we'll just do one more configuration check. Let's just go ahead and make sure that the VLANs are active on our access layer switch. So it looks like we've got, in essence, what we described, kind of the setup of this particular topology, regular spanning tree running, and the switches that are supposed to be the roots are the appropriate roots. So our next step would then be to go ahead and kind of migrate this configuration to our multiple spanning tree configuration. All right. Now, as it is right now, we have 5 active VLANs in the lab. We're running PVST plus, which means per VLAN spanning tree. 5 VLANs are going to translate into 5 spanning tree instances. And we see that in the Wireshark capture here. It's pretty active. We're still getting a ton of those Bpdus. We've captured over 1,700, 1,800 different Bpdus, pretty much, outside of the CDP and the VTP stuff, but pretty much, you know, well over 1,500 Bpdus since we started going through this particular exercise. So we're going to go ahead and configure all 3 switches, switch 1, switch 2, and switch 3, to be part of the same MST region. We'll call that MST region CCNP. We'll have the same revision number, which is going to be revision number 1. So let's go ahead and execute the commands. Let me make sure I'm in, because I can do this with my macro here. So I'm going to go into all my switches, and I'm going to say config T, and I'm going to say spanning-tree, MST configuration, and then I'm going to say name CCNP, and I'll say revision 1. All right. Now it's easy when I have a scripting tool like this. I can kind of push out the config. Obviously, if you were doing this on the switches independently, you'd want to make sure that you were basically duplicating this configuration on all of the switches. So we can see switch 1 has the config, switch 2 and switch 3 have the config now. Makes my life kind of easier when you can push out these configs to all the devices at the same time. So we've in essence set up the region, but we're missing a big component of this, right? We have to map VLANs 2 and 3 to an instance, and we have to map VLANs 4 and 5 to an instance. In this case, we're just going to use instance number 1 and instance number 2. Now, if you recall from a previous discussion, the extended system ID format that we have for spanning tree typically would carry the 12-bit VLAN ID field inside of the Bpdu as part of the bridge ID. In our particular case, because we're not going to be running spanning tree on a per VLAN basis, we're going to be running spanning tree on a per instance basis, then the instance number will be carried inside that 12-bit field instead of the VLAN, which means that we can actually mathematically have 4,096 different instances. All right, so let's go ahead and push out this config as well. We want to make sure that these configs are consistent and they're accurate, because this again is where the hash is going to be calculated, and if the hash doesn't match, then the switches will not belong to the same instance. So we're going to create instance number 1. We're going to say go ahead and put VLAN 2 and 3 in that instance, and instance number 2 VLAN 4 and 5. All right, we'll send out that config. All right. Now, just to be clear, if I come in here and I say spanning tree MST configuration, you can see that I can create 4,095 instances. All right, pretty much kind of the same concept as creating the individual VLANs, but we're just creating an instance and we're mapping particular specific VLANs to a particular instance. Now, if I go back to my Wireshark here, you can see that I'm still running PVST+. So even though I've gone through it, I've configured MST, I've set up all the properties of MST, it's actually not active until I've gone in and made sure that the configuration is complete, which is nice because I can go in and I can configure MST and I can set it all up, make sure it's all working before I decide that I'm going to flip it over and turn it my PVST domain into an MST domain. So at this point, MST is configured with all the instances. VLANs 2 and 3 belong to instance 1, 4 and 5 belong to instance 2. Now there is another instance that was created. It's automatically created and it exists no matter what. That's instance 0, because we have a lot of VLANs that have not been mapped to an instance and they have to be mapped somewhere. So instance 0 will always exist, and any VLANs that are not mapped to a specific instance will get mapped to instance 0. And we can, by the way, control instance 0, who becomes the root for instance 0, just like any other instance. Speaking of that, let's go ahead and make switch 1 the root for instance 1, and let's make it the backup for instance 2, and then let's do the opposite on switch 2. So spanning tree MST, we're going to say instance 1 root primary, and then we'll say instance 2 root secondary. And again, this won't have any effect on our current domain because that's regular spanning tree. Spanning tree MST1 root secondary and MST2 root primary. So the nice thing about this is that I don't have to do this anymore per VLAN. I can simply enable these MST configurations per instance, which then the VLANs get associated to the instance, and they in turn join that particular topology. So in this example, we changed the MST priority using the primary and secondary commands. Just like before, we're going to set priority values based on those numerical functions that we talked about in the last exercise. So switch 2 became kind of the secondary for MST1 and became the primary for MST2. The last step is to just turn on multiple spanning tree. So let's make sure all my prompts are clean here. And I'm going to go in to my script, config T, spanning tree, oops, trying to use tab completion, spanning tree mode MST. All right. So this will then enable those switches to run multiple spanning tree. Now, if I go to my Wireshark capture, you should see that things will change and we'll start to see MST information as opposed to PVST plus. So actually right here was our last PVST plus message, and now we're seeing spanning tree, spanning tree, spanning tree, but we can also see MST listed here. So this was PVST plus, and then this was our first instance of MST. We can also see that the amount of traffic is significantly less. Well, not significantly because we don't have a lot of VLANs, but you could see how it could be if you had 20 or 30 or 40 VLANs in the topology. So changing this STP mode to MST before doing any actual to VLAN to instance mappings is really not advisable, because every change in the mapping is going to result in kind of a recalculation of the spanning tree topology. So it's better to get everything configured and set up, even go through, and you can go through the switch and you can actually come in here and say show MST configuration, and you can see how everything is configured before you decide to enact that particular configuration. So you can go back and double check and triple check everything before you get into the actual turning the protocol on. All right. A switch cannot run MST and PVST plus at the same time. So if I come in here now and I say show spanning tree, I can see that I am now running MSTP. Now there's a couple of things that have changed here, right? We can see that we have well, let's do a show spanning tree. Let's go to switch 1. And let me do a show spanning tree summary. So you can see that we're running MST. We can see that this particular switch is the root for instance 0 and instance 1. And we have our typical spanning tree toolkit. Now, what is the underlying algorithm for multiple spanning tree? I mean, obviously we still have to make a decision on who the root is, what the root ports are, what the designated ports are, what the non-designated ports are. But in this particular case, it's PVST or rapid per VLAN spanning tree. So MST uses the RPVST plus protocol, rapid spanning tree. So convergence is going to be very fast. Things like uplink fast and backbone fast are going to be enabled by default, and so on. So we have 3 MSTs. We have 8 ports forwarding, 8 ports active. Obviously, we don't have 8 ports on this switch, but again, that's a viral thing, IOSV thing. Okay. So like I said, if I come in here and I do a show spanning tree MST configuration, I can see what that configuration looks like, and I can go through and verify that configuration prior to actually enabling the protocol. All right. We can see that VLANs 2 and 3 are mapped to instance 1. VLANs 4 and 5 are mapped to instance 2. All the other VLANs are mapped to instance 0, or what we call the IST. We talked a little bit about that in the lecture portion. To verify the currently applied MST configuration, we would use the show current command in the MST configuration mode. If I want to see what the pending MST configuration is, I could use the show pending command in MST configuration mode. In this case, so if I come in here and I say config T, spanning tree, MST configuration, show current, in this case, and show pending, in this case, it's going to show me the same thing because we already applied this configuration. but that's also something that you can do. You can, current would be what's presently active, right? Because when you're in MST configuration mode, nothing gets applied until you get out of MST configuration mode. So you can go in and you can start to make modifications and do your changes, and then you can kind of compare where we are today versus where we will be if we were to apply those particular changes. The next thing we want to do is we want to verify the message digest. So I'm going to use the show. In fact, let's do this this way so we can kind of just alt-tab between these. I'm just going to run a show command, show spanning-tree, and MST configuration, and I want to see the digest. All right, so I'll run this command, and what I should see as I flip through here is that digest is the same for each switch. All right, this digest, as I mentioned, is a hash, if you will, of the MST configuration. Since the MST configuration is identical on all three switches within the region, the digests match in this particular case. A mismatch in the digest would indicate that the VLAN lists don't match between the switches. The digest would, be different in that case, and then we would have kind of a separate region, if you will. The switches would assume that there's just a different region that we're connecting to. The pre-STD digest, which is the one listed below, that's the Cisco legacy pre-standard implementation of MST. Cisco actually developed their own proprietary version of MST called Mistp, which had kind of the same principles of MST, so that's why you see two different digests here. All right, so if I go into, say, for example, switch 3 now, and I do a show spanning tree MST1, I can see the instances and the layer 2 convergence on the switch itself, and I can also do that thing for 2 as well. Now notice here that a couple of things are different, right? The output here is very similar, right? The root bridge is elected based on priority and MAC address. Priorities are established the same way. MAC address is, of course, the burned-in address. But notice how we have different costs here, right? These are what we call the more modern approach to path cost, which takes into account faster link speeds and so on in more modern network topologies. You can actually switch back and forth between what cost format you'd like to use, the long format or the short format, but in this case we're simply using the long format. So we can see that who the root is for MST1, the root is switch 1, who the root is for MST2 is switch 2, this is switch 3, and we still have root ports and alternate ports, which are non-designated ports. So we don't see anything different from that perspective. The only other major difference is the actual port costs. Port priority is the same though, right? Port priority allows us to identify in a tie-break scenario which port is going to be preferred. Remember we talked about that in our previous lesson where we said, okay, the advertising port priority and number will let me determine as a tiebreaker which physical interface I'm going to use to communicate to that particular client, okay? So just as a I'm not going to make any changes here, but let's say, for example, I went into config t interface gig 03. I would just say spanning tree. Now, we're not applying this to a VLAN, we're applying this to an instance, and then we would set the port priority. So everything that we used to do on a per VLAN basis, we're now doing on a per instance basis. Let's take a look at the Bpdus as well, right? We can see that in the Bpdu, multiple spanning tree, but you notice the Bpdu type is listed as rapid/multiple spanning tree, which, by the way, kind of demonstrates that concept that multiple spanning tree runs the underlying rapid spanning tree protocol for its algorithm, which means that overall we're going to see the same format, right? We see the same flags that are used for negotiating the spanning tree topology. We see the same format for bridge ID. This happens to be, for instance, 0, which is actually another interesting point here, right? You'll notice here we don't see any BPDUs for any of the other instances. Look at this middle number right here. It's all 0, all the way down. So we're actually not generating BPDUs for any other instance except for IST, which is the kind of the primary instance, if you will. So that's kind of an interesting concept. But what about the other VLANs? Well, that's what this MST extension is for, right? This tells me the regions. It gives me the root information for each of the instances, the individual instances. So this BPDU carries everything that we need to know about all of the different instances within the topology. Here's our IST information, right? What's the IST bridge ID for this switch? This is switch 2. What is the MST configuration name, the revision number, the digest? Remember, the digest is a manifestation of the VLAN to instance mappings that we have configured. And then we can see, okay, for region 1, this is the root switch, switch 1. For region 2, this is the root for that region, switch 2, and so on. So even though we're not sending out individual BPDUs per instance even, we're sending one instance, one BPDU, it is going to describe all of those instances that exist. All right? So just like with regular spanning tree, once the root bridge has been determined, we have to go to our non-root devices and we choose the lowest root path cost. Then we choose the lowest sender bridge ID and the lowest sender port ID. So lowest path cost would be in the event that we have multiple paths to the root, but there isn't a tie. Lowest sender bridge ID would be if I can go to switch A and get to the root and it costs me 10, and I can go to switch B and get to the root and it costs me 10, I'm going to pick the switch with the lowest bridge ID. That's the direction I'm going to go. Lowest sender port, we talked about that. That's parallel links to the same neighboring switch that have the same path cost. I'm going to choose whatever the lowest sender's port ID is. That's part of that port priority configuration. Now we can assign higher sender port priority values, which would mean a lower numerical value to interfaces. And as I demonstrated, it's just basically the spanning tree MST instance port priority command. All right. For the instance variable, we can specify a single instance. We can generate a range of instances that are separated by a hyphen, or we could actually do a series of instances that are separated by commas. The range itself, as I demonstrated, could be anywhere from 0 to 4094. For the priority variable, the range is 0 to 240 in increments of, actually in this case, 0 to 224 in increments of 32. It depends on the switch type. Some switches are 0 to 240 in increments of 16. In this particular case, 0 to 224 in increments of 32. The default is 128. The lower the number, the higher the priority. Remember, lowest always wins in spanning tree. All right. To verify the port priority settings, we did that. Again, we can modify those values. So let's go into switch 2 in this case, or switch 3, excuse me, and go into interface gig 02. And let's do a spanning tree for MST1, and we'll just change that port priority to 64 in this case. All right. Now, it's not going to have too much of an effect on our topology because we don't really have any tiebreakers. But if I come in here and I do a show spanning tree MST1, we can see that the port priority was changed based on that configuration change. All right. Same again. Path cost is ultimately going to be the decision factor here because we don't have any redundant paths. So what about if I want to modify path cost? Right. The path cost function provides the same functionality in MST as it does with any other spanning tree topology, right? But port costs are configured per instance, all right, not per VLAN, just like we saw with the port priority. So just like with any other spanning tree, the path cost default values are derived from the speed of the interface. And if a loop occurs, we just simply use the cost to select which interface ends up going into a forwarding state. So if I go into a switch, for example, and I look at the cost for these links here, we can see that we're using these particular cost values. Now, the cost values are different here. In fact, let me pull up a graphic. So I just pulled up this graphic here, and it kind of talks about what are the new port path cost values. In original 802.1d, we supported a 16-bit value for path cost. So that would go from 0 to 65,535. The problem is that would limit us quite drastically to setting some of our higher speed ports to look the same, basically. So with the newer versions of Spanning Tree, they went to a 32-bit wide path cost value, which allowed us to kind of derive these new common values, if you will. Now we're using 1 gig links in our case, so 20,000 is the standard range, but we can see we can go anywhere from 1 to 200 million in this particular case. If I go back here, I see the 20,000 as suspected. So these are already selected values for those individual speeds, if you will, but it's an arbitrary. It's not completely arbitrary, right? It's decided based on link speed, but you can certainly change those values to whatever you want them to be to affect the overall election. Now, as far as MST, just like any other spanning tree configuration, we use 4 criteria to choose the best path: the lowest bridge ID, the lowest route path cost, the lowest sender bridge ID, and the lowest sender port ID. All right. We can assign lower cost values to interfaces if we want to select those first, and higher cost values if I want to select those interfaces last. Now, if all the interfaces have the same cost value, MST puts that interface with the lowest sender port ID in a forwarding state. It blocks other instances as well. So we can change this with cost. We'll take a look at this. In fact, let's go ahead and go into switch 3. And we're going to change the cost here, config T interface gig 03. And again, it would just be spanning tree MST 1, and we'll just simply say cost, and let's just make it 40,000 in this case. Do show spanning tree MST 1, and we can see now that the cost is 40,000. So it's still a relatively easy thing to modify. And in this case, actually, we end up, it still is the root port, because again, we still have other path costs in between that we have to account for to get to the root for MST1. All right. So you would adjust these numbers and modify these numbers based on whatever your particular goal is. All right. So that concludes our discovery on MST. We'll get back into a little bit more lecture, and then we'll see you guys in our next lesson. So the last section that we'll talk about in this particular chapter is what is PortFast and what is Bpdu guard. And there's a bunch of different toolkit options that you have with Spanning Tree. To list them off consecutively, these would be the 2 most common ones. I would say there's one other one that you would see on a common basis, and that is root guard. You might see Bpdu filter from time to time if you're connecting your layer 2 domain to a domain out of your care and custody or your control. But there are many different options for the Spanning Tree Protection Toolkit. Number 1, you have PortFast, Tube, Bpdu guard, a Bpdu filter, ether channel guard, loop guard, root guard, backbone fast, uplink fast, and a few others, right? And then outside of the Spanning Tree Toolkit, you have something called UDLD as well, unidirectional link detection, that allows you to identify unidirectional links that could cause Spanning Tree loops as well, even though that's not technically part of Spanning Tree. We're going to explore these 2 features because these 2 features are certainly the most common that you would see, PortFast and Bpdu guard. So if you're looking at a port and how the port functions, how it operates, the port is always going to start in a blocking state. Now, if I plug a PC into that port, the first thing that that switch port's going to be looking for is, hey, I need to get some BPDUs, because I can't decide what to do with the port until I figure out what's connected to the port, how the port is functioning, and how it's operating. So I need to get some BPDUs. Unfortunately, a PC is not going to send BPDUs because it just doesn't generate BPDUs, right? It's not a switch. It's not running spanning tree. So the switch has to decide, well, what am I going to do? If I'm not getting BPDUs, how can I determine whether or not this port is going to cause a loop in my topology? So what it does is it goes through the max age timer. And it says, all right, if I don't get BPDUs for 20 seconds, I'm going to assume that I can then transition to the next state, which could be the listening state if you're running a regular spanning tree. So for the first 20 seconds, the port doesn't do anything. Then we transition to the listening state for another 15 seconds. Now, if I had plugged a switch in or any device that would be propagating BPDUs, I would have skipped that blocking state altogether and immediately gone into the listening state. But again, I'm not receiving BPDUs in this case. I'm going to stay in the listening state for another 15 seconds, and then I'm going to transition to the learning state for another 15 seconds. At that point, I'm going to make a decision. Do I go into the forwarding state or do I go into a blocking state based on the port role that I've determined for that particular interface? So it could be anywhere from 30 seconds to 50 seconds before the port even becomes usable and transitions to a forwarding state when the port becomes active. And during that process, by the way, the PC thinks the link is up. It's doing its DHCP discover. The DHCP process is failing, and we're getting limited or no connectivity on the PC. So how can we kind of bypass all of this? Well, that's what PortFast comes into play. When I configure PortFast on an interface, it basically instructs the switch to go ahead and place that port into the forwarding state immediately. Right? So we would configure PortFast on our access ports. Now, it does not disable spanning tree. A PortFast enabled port will revert back to a normal spanning tree port if it happens to receive a BPDU. So if I have an access port configured as PortFast and I unplug the PC and I plug in a switch, there may be a temporary loop while the switch figures out that there's a device connected that's generating BPDUs, but the switch will eventually, that switch port will eventually revert back to a regular spanning tree port, and it'll go through that whole process of listening, learning, etc. All right. Now, BPDU guard is typically a feature that I would implement on my edge ports as well, on my access ports, to protect against rogue devices or a malicious device that's trying to spoof, send in superior BPDUs and act as a route so that we can insert ourselves into the conversation and so on. BPDU guard is a very, very simple configuration. Once it's implemented, and there's both of these can either be implemented globally or they can be implemented on the interface. But once BPDU guard is implemented on an interface, if that port receives a BPDU, it goes into an error disabled state, meaning that essentially the port becomes unusable. And the only way to recover from that is to make sure the BPDUs no longer exist and then shut down the port and bring it back up, or use some sort of error disable recovery mechanism that allows us to recover the port within a certain amount of time, if you will. Okay? So there's several ways that we can kind of deal with error disabled ports, regardless of the reason that it becomes error disabled. There's lots of reasons why a port might become error disabled. All right. Typically, we would use BPDU guard in combination with PortFast as a general security practice. Because look, if it's a PortFast enabled port, it means that there are not supposed to be any devices connected to that port that should be generating BPDUs. So naturally, if I get a BPDU, then somebody's violating the configuration policy, and we need to go ahead and block that particular port. And it's a really simple configuration, very, very easy. Like I said, you have two different options with regard to doing this. You can do it in global mode, or you can do it in interface configuration mode. The impact and how it functions is basically the same, but there are a couple of minor differences between implementing this in global mode versus interface mode. All right. So they go through a scenario here and talk about why PortFast might be used and so on. We've already discussed that. So how do I configure these options? All right. Now, if I decide I want to do it on the interface, I simply go into the interface and I say spanning tree PortFast. And if I want to go ahead and enable Bpdu guard, it doesn't have to be enabled with PortFast, but if I want to, I say spanning tree Bpdu guard enable, and I'm done. This is both of these features are now unconditionally enabled on that particular interface. If I decide to do it globally, which is the next box down, spanning tree PortFast Bpdu guard default and spanning tree PortFast default. In this particular case, these features would only be enabled, because it's kind of scary if you think about it, right? You're saying, oh gosh, I'm implementing these features as a default. What about my links that go to other switches? What about my links that might actually get Bpdus? Are they going to error disable? Well, when you implement this globally, the switch only enables the feature on non-trunking ports. So that should exclude all the switches, because most of the time those switch ports are going to be trunked ports and not non-trunking ports. All right. But what about the ports that are trunks that are not connected to another switch? Maybe it's a port that goes to an ESXi host or a VMware server or a router on a stick. Well, I want maybe potentially PortFast configured on that port. I would actually have to go into the interface and say spanning tree PortFast trunk. I would add the trunk keyword to make sure that spanning tree is unconditionally enabled on that trunk port that goes to a VMware server or some device that's not generating Bpdus. All right. You can do Bpdu guard without PortFast if it's enabled on the interface specifically. Notice that the PortFast keyword is part of Bpdu guard globally. That means that Bpdu guard is only going to be enabled on PortFast ports. And PortFast would only be enabled on trunk ports in this particular case. So it depends on what your overall goal is. Do I want to enable this unconditionally on a port, or do I want to enable it only if the port is not a trunk port? And those are the two different options. As far as the end result, though, it's essentially the same with regard to putting the port into a forwarding state immediately, and if the port receives a Bpdu, it's going to error disable. That doesn't change regardless of how you configure it. Again, remember, enabling PortFast on a port does not disable spanning tree on that port. All right? But there is, again, the potential of a temporary loop while the switch tries to recover and figures out what to do with that port. I've never seen it actually occur where the loop basically causes the switch to fail before it can even respond to the Bpdu and make it a normal spanning tree port. Usually I see the ports go, recognize the Bpdus pretty quickly, and they go into blocking mode if we have Bpdu guard enabled, or they go into the blocking, listening, learning, etc. Okay. Show spanning tree summary allows us to verify that these toolkit features are configured, whether it's Ether channel guard or PortFast or Bpdu guard or Bpdu filter. We can see them implemented on either the interface, or we can see them implemented in the show spanning tree summary command. And I can also see which ports are enabled for PortFast, for which VLAN, etc. So lots of options to verify the features, right? Whether it's Bpdu guard or PortFast default or Bpdu filter or ether channel guard, whatever it might be. Pretty much the only command that I use to do this verification is show spanning tree summary, and I'll just see what features are enabled, and I'll be able to identify what ports those are enabled on. As a best practice standard, I typically will just do the global commands, enable PortFast on the globally on the whole switch, and then I'll go in and set the PortFast trunk feature on any trunk interfaces that go to devices that are not switches where BPDUs are not being received, and then we'll call it a day. All right. All right. Spanning tree PortFast, like I said, enables PortFast on the port. Spanning tree PortFast default is a global command. Enables PortFast on ports that are not trunking. Spanning tree Bpdu guard enables the Bpdu guard feature unconditionally on a port. Spanning tree PortFast Bpdu guard default, a global configuration command that enables Bpdu guard only on PortFast enabled ports, which would then be ports that are not trunks. And then we use the show run interface, show spanning tree, and show spanning tree summary commands to verify the operation. Okay? How long does it take a standard STP port without PortFast to progress from the blocking to the forwarding state? Well, this is kind of a trick question. I would say the answer is 50 seconds, but it depends. It depends on whether or not there is a device generating BPDUs or not. Because if I get a BPDU, it's going to be 30 seconds. If I don't get a BPDU, it's going to be 50 seconds. So we'll assume it's a port that a host is connected to. In which spanning tree protocol state does the port listen to BPDUs that it receives and listens for new topology information that would cause it to transition back to the blocking state without populating the MAC address table? That would be the listening state, not the learning state. Okay? I mean, the answer was in the question a couple of different times. So just to wrap up this particular lesson, which is the calculation used to determine the root port in the spanning tree calculation? The port with the fastest speed, the port that the neighbor switch will forward traffic to, the port with the lowest cost to the root, ding, 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 the first port that becomes active. So it's the port with the lowest cost to the root. Let's try that again. There we go. In the spanning tree protocol, what is the default factor that determines the cost of the path associated with a link? The default factor that determines the cost of the path. That would be the speed of the link, right? The type of link does directly relate to the speed, but if you change the speed of the link, it will change the path cost. All right? When they say type of link, they're not referring to gigabit or Ethernet or fast Ethernet. They're talking about point-to-point or shared, which doesn't have any effect on the actual cost of the port itself. It's the overall speed of the port. Which two of the following options are IEEE variants of the spanning tree protocol? So an IEEE variant would be MSTP, multiple spanning tree protocol, and I'm curious, I guess STP, right? Because PBST Plus and Rapid PBST Plus are both Cisco versions of STP and MSTP. And VRRP is a first hop redundancy protocol. I'm guessing that's what they're trying to get to there. Which of the following options is not a port state? A rapid spanning tree protocol port state. And that would be blocking. It's kind of weird because discarding is technically blocking. We're not forwarding frames, but they don't have the blocking state anymore in rapid spanning tree. They've renamed it to the discarding state. All right. Which type of rapid spanning tree link is full duplex and assumes that the port is connected to a single device at the other end? That would be a point-to-point link. In MST, which of the following options is the first criteria used to choose the best path? To choose the best path, it would always be the lowest path cost. Just like in regular spanning tree, the best path is whichever one has the lowest cost to the root. The tiebreakers would be lowest sender port ID or lowest sender bridge ID, but the first choice is always going to be what is the least cost path to the root. All right. Which of the following options is the protocol that will prevent a bridging loop if a Bpdus are received on an interface that has the spanning tree calculation disabled? Well, that would be Bpdu guard, right? We never really truly disable spanning tree on an interface, but PortFast could cause or could allow a couple of Bpdus to be ignored while the port is reverting back to a normal spanning tree port. So we would want to implement Bpdu guard to protect against that, because as soon as I get a Bpdu, the port error disables. Which command can you use to verify the MST port cost for instance 1? Show spanning tree MST1. We would just basically replace the keyword VLAN with the keyword MST to identify that we're trying to verify the MST configuration for instance number 1 in this case. Which is the calculation used to determine the root port in the spanning tree calculation? Is it the port with the fastest speed, the port that the neighbor switch will forward traffic to? Oh, these are
yeah, you're on the duplicates.
The duplicates again. All right, excellent. Well, that concludes that lesson. Let's go ahead and get into the next lesson.